I'm very happy to welcome you back to Volume 3, where we will finish procedural placement of our modules. This time, we will focus on roof set dressing as well as placing windows and doors. We will face new challenges and learn how to solve them, such as procedurally assigning the correct scale to ensure that all of our modules can fit to the desired area perfectly, as well as dealing with more complex combinations of modules. All the assets are included with the course material, and I just can't wait to start. So I hopefully see you soon, and we will continue making our building generator more awesome.
Hello and welcome back. In this video, we're going to place our roof modules, and here I just want to show you, this is a file from the final generator, I just baked it in a VGO, but I want to show you how the modules look in their final result. So what we have is we have a tip, we have an extension body, so this rail, and we have the front tip, as well as we have the top rail, windows like this, and we have the chimneys. So those are the modules that we're going to operate. Feel free to have a look at them. I attached the OBGs for you to use, or feel free to create your own version. And in this video, we're going to generate the pivots positions to place those modules procedurally. So let's dive into it. So here is our file as we left it in the previous videos. And today we're going to just use the roof base. So let's create a new null. Let's call it in. Connect our roof base. Collapsed into a subnet, which we will call roof modules. And we're going to color it into the dark blue and dive into it. So here, what we want to do is, if you remember, if you go to the spreadsheet, we had a roof ID. And right now we're going to treat every single roof, but we need to know what is the maximum ID number, because when we create our for each loop, we need to know where to stop. So let's bring attribute promote. And we promote from primitive to detail our roof ID. So roof ID. Did I spell it correctly? Yes. And we will change a new name. We want the maximum, and we will say max roof ID. And we will rename the notice as well. I'm going to say promote roof ID. Awesome. So the next step is what we want to achieve is, like, roofs never just end so abruptly. Let me show you. So if you look in the real wooden house, they always have a bit of an extension to their roofs. Yeah, and here as well. Yeah, this for example illustrates it really well. So that is what we want to imitate as well, and note that on it kind of extrudes from the body both front and the sides. So that is what we want to imitate as well. So let's create another null. Collapsed into a subnet, which we will call just extensions. Extensions. We will color it so it is easy to find for us in the future. And here, let's rename it to in. First thing first, we want to get rid of the platforms. So blast. And we will delete everything that doesn't have a roof ID, because if you remember, we assigned a roof ID -1 to, or so I thought. Oh, did we delete the original? Wait a second, go up. Yeah, make sure to uncheck delete original. We really want to keep the roof ID numbers. So yeah, so once we did it, I will say delete platforms, because we do not need them. We're only gonna use the roofs themselves. So all the preparations are done. Now we are ready to create a for each loop. And we will say for each number, we're gonna go from 0. And that is why we promoted our roof ID, because we're going to grab the detail from the first input node, and we're going to say that it is called max roof ID and 0. So let's check if it works. Yeah, it works nicely. We will call this extend, and let's color it as well, so we know it's the main one in this subnet. Let's dive into it, and we want to locate the roof that we're currently running over. So locate, and what we want to do here is we want to say that the roof ID is equals to stamp up for value 0, and deleting selected and it's primitives. Something is really fishy going on here. Why our sites do not have ID? Huh, that is interesting. Sites, they all have 0 ID. Okay, that is a mistake, which we will have to check. So let's check 6. All the sites have 0 ID. Huh, interesting. Okay, this is a mistake we have to fix. So let's go back to roof base and let's find our sites. Okay, it's in the roof extrusion, merge and sites. Okay, where is the site? So no site, sites. Okay, this is a site and we want to make sure that it has correct roof ID. So let's copy roof ID and we want the same roof ID as the stamp value in here. So this is a small mistake we had. Let's create an attribute called site. It's primitive and we will say value 1. So now, and let's say it's an integer, I think. Yeah. So yeah, now we separate the sites. Thank you. And we also want to say no sites, and delete selected. So yeah, that is the one we're going to work primarily with. So what are the cases that we want to avoid? Let me show you in another file. Yeah. So the first one is sometimes we have roofs that touch, and there is like a check, which we will call check for touching roofs. And if I disable it, you see that this start intersecting. Maybe you'll see better with the light on. Yeah. So as you can see, the start intersecting. That's a check that will make us avoid the extension where the roof touch. And another one we want to avoid, which we will call check for stairs, is whenever we have a stair. Well, here, like as you remember, they're going to be placed a walkway and a stair. We want to avoid the extension because in the front, because otherwise it will just intersect with our stairs and it doesn't make sense construction-wise. So those are 2 cases that we want to avoid. So let's implement them. And we will start with initializing the attributes we're going to need. So let's grab attribute create and we will call it attributes initialize, attributes init, and we will create an attribute for every case. So we have only 2 cases, so we will have a case of touching roof, and it's an integer. It's going to be like just booleans basically for us. And the other one we will call stair point. So also an integer. So those are 2 cases that we can have, and those are just booleans. We're going to have only 0, which is not true, or 1 if we want to do something. So, but first we need to assign those attributes because right now they always 0. So we're going to compare our roof to the other roofs. So we want to create a new blast, and we will call it non-selected. Non-selected. So those are the roofs that are not selected. So the first thing first, we will create the touching roof identifier. And we will call it check for touching roofs. And we don't want to check for everything because, for example, here we have the ray point. And sometimes we can have ray points of another roofs. However, we do not want to consider those. We do not want to check for rayed points. So in this case, we only want to check for the sides. So let's do that. So let's create a wrangle, which we'll call delete ray points because we don't want to consider those. Let's bring it bigger and we just say here ray points shouldn't be considered. Yeah. And we say that if ray point is equals to 1, so if the point we're currently checking is a ray point, then we want to get it neighbors because we want to delete the whole bunch. We want not to delete only the ray point, we also want to delete the bottom neighbors, so we're kind of deleting the whole side. So 0 pt_num. We just say delete bottom neighbors. We only want to delete the bottom ones. So vector position, we will need to position to identify that. So for each, and we want to grab our neighbors, so nice, and we just identify the position. We grab it from our neighbors. So p n And we say if the position of our neighbor is smaller than the position of the current point, then remove the point. Remove point 0 and n. And after that is done, we can safely remove our point that we are checking now, because it is array 1, so we don't need it. So once we did it, so accept, as you can see, all this body disappeared because it is an arrayed body. So yeah, after that is done, we can connect it to our second input to check for touching roofs. Since touching roof is a very specific case, which I showed you previously, we would say that array points shouldn't be considered again, because like we will never see the extension there, the front one, and we never will extend it to the front or the side. So array points should not be considered. So first thing first, we need to grab the neighbors again of every point we're going to check. So 0 pt num. We also want to check whether its neighbors are array points. So we will say found array p for array point 0. And we will check every neighbor. We also want to know, is any of the neighbors is actually array point. So if point 0 array point attribute of our neighbor is 1, so we are one of our neighbors is array point, we just say that yeah, we found it. If we don't have any array points, so found array p is equals to 0. Now we want to check for other roofs. So what we're going to do is we're going to run like a PC open again. So int pcloud. When I say PC open, I'm going to check the first index input and the same gist, very small radius, because we just want to see whether it touches with the other roof. You say see if it touches the other roofs. And we say if PC num found of the pcloud is bigger than 0, so something was found, it indeed touches something. We just say that touching roof, roof is 1. So the attribute we initialized earlier is now 1. It's true. And we don't want to apply it on itself. We also want to apply it to its neighbor. What we will say is for each. We'll run through the neighbors again, and we will grab the position again. So p of the neighbor, and if the position.y is equals to the position py, so basically we are grabbing the bottom neighbor. So that's what I will actually write. Apply for the found point and its neighbor and its neighbor on the same height. The bottom. Technically, the top points will never find anything. That is why it's like only bottom. So yeah. So if they are the same, so technically, like if I don't know, this point found that it touches someone, then we want to make sure that this point also doesn't extrude down. That is why we are checking for the same position and y. So if it is true, we also set that point that it is a touching roof point. Touching roof. That is why we had to initialize the attributes earlier, so we can set attributes with a set point attribute expression. So 1 and set. So apply, accept. So in this case, we're not going to have anything. So let's check. All of them should have state 0 points. Touching roof. Okay, for some reason this one's assigned 1, 3, 2, and 1. Our locate is this one. Why this one is different? So we can go up. And we will just do 0. Okay, it's just yeah, subnet sometimes bugs out in a weird way, like it shows you that like some things are a bit different. So I'm not sure if this is because of the naming, so I might try to just name it to extend, and just rename it in here as well. Extend. And here as well, extend. I'm sure that will help. Yeah. And let's grab this one again. And don't pin. Yeah. it's a bit weird. Because when we go up, it's all correct. So let's just cut it out, keep it for 0, then it doesn't bug out, and I'll just store this expression in a transform for now. So let's go back into extend. So right now it should be all correct. Yes, that is correct. And none of them should have had touching roof assigned. Yes, all correct. Beautiful. So the next step is to consider the stairs point, which we will bring with the object merge node. We will take it from the stairs and stair point. Let's color it so we can see it, and we will call it stairs point. Since sometimes our roofs can feature a platform, we need to make sure to lift it so our PC Open can find it. So let's bring a transform node. And what we want to do is we want to look at the locate, and we want to lift it to the same Y position. So what we're going to do is, in Y, we're going to write the following expression. So we're going to write minus $y maximum. So we're going to bring it down. And then we're going to say that lift it to the same amount as the bounding box of our attribute initialize. Let's take that one and dy minimum and apply and accept. And as you can see, we lift it just to the same y. The next step is what we want to do is, like if we look at all the roofs we have, this roof is definitely much higher than the possible stairs, because stairs is going to be like somewhere here. So this is definitely much higher than we need to consider. Therefore, we will need to add a switch with a null. So we're not going to consider the stairs if our roof is too high. So what we're going to write is we're going to copy here this bbox, apply accept, and we're going to say that check only if it's smaller than 5. So, and that is not true, therefore it should be null. But we don't only want to consider the stairs. In the next attribute triangle we're going to create, we also want to check for perpendicular roofs, because in this case we're going to check whether the roof has to like extrude to the front. But sometimes roofs can feature like this one, and here can be another roof. However, they do not merge, but they're like perpendicular to each other, and that's when we also do not want to extrude the roof. Therefore, we also need to merge our stairs and ray points. And the way we're going to determine whether they are indeed perpendicular is just by looking at their normals, as they already have the correct normals for us to check. So let's bring the wrangle node. We will connect our initial roof, the one we are checking, and we're going to connect our merge node into the second input, and we're going to call it check for stairs and perpendicular roofs. So let's bring it bigger. And here, what we want to do is, first of all, we want to find all the closed points. So we're going to say pcloud, but it's going to be an array because we're going to grab every point into an array. We say pc find. From the first index, we want to look at the position. From the current position of our point of 0.3 radius, and we need to only find 1. And then if the length of our array, so technically we'd actually, yeah, actually we could have used PC Open as well, but it doesn't really matter which one you use. So if there was something that we found, first of all, we want to get point normal, because that's how we're going to see whether it's perpendicular, because even with the stairs, let me apply that and accept, I want to show you, so even when we have the stair point, let's imagine that this is actually a valid floor, and for example, the stair starts here. We only want to check if they're perpendicular, because sometimes the stair point can be here and the roof actually looks that way, like this one, and the point is here, then the roof technically should still be extruded, because we only want to check if the normal of this is perpendicular in x and z to stairs point normal. So that's what we want to do. So let's grab the normal. So we're going to say point 1 and then we want to grab the pcloud 0. So yeah, actually we do need the array, otherwise you have to PC iterate. Vector cross. So now we want to find the cross between the normal and normalized version of our own normal, and we want to say that it's a round one just in case. So yeah, And then we say that if normals of the roof and stair point are not parallel, so if cross is not equal to 0, 0, 0, which means they're parallel, we want to grab the neighbors. And it's an array with our neighbors function from the current point. So what we want to do is we want to assign the top point to be the stair point, because then we will tell it not to extrude anything. So for that we will need a relative position, because we're going to use the bounding box to determine the top point, and the position. So for each int n in neighbors. So the position is point p, and we're going to grab the neighbor. So relative position is relative b box inside of our geometry, so inside of the first input and position. So if relative position y is 1, so if it is a top point, like a point which relative position in the big box is 1 in y, then we will say that it's a stair point. So set point attribute, and it is a stair point. Stair point, our neighbor 1, and set. Apply and accept. So right now, none of them should have the stair point. You see, yes, stair point is none. However, if we change the switch, yeah, the fifth became a stair point. So why did that happen? So let's actually check. We have this, and this point was found. Was found by point number 2. So what point number 2 did is it looked for its neighbors, so 3 and 5, and it was looking for the one on top, and so okay, 5 is on top, and that's why the 5 was assigned stair point and not the second one. So that is how it works. So let's invert our switch again back. So now it is time to extend the roof, so we need another wrangle, and here I will say that it's an extend roof. So here, based on the 2 attributes that we created previously, we're going to extend the roofs. So let's do that. So first we will need to grab again neighbors. For every point we're going to check. So neighbors. And we will need to the position. So now first of all we're going to extend the front extension. So first of all, when do we not make the front extension? We do not want front extension if it's a array point, if it merges with another roof, so it should be a 0. And it should not be a stair point, because if it's a stair point, it means it's either close to the stairs or it's perpendicular or close to a perpendicular roof. Then we don't need the front extension anymore. So let's grab the stair point. Stair point is also 0. So if both of those are satisfied, we can start writing the code. So we say we will need multiple attributes. We're gonna grab the attributes of its neighbors. So we will need variables to store them. So we want a array attribute, and we want a stair attribute. We want to grab those 2. We also will need to found, and then for each one, we're gonna go through the neighbors. And we're going to grab the position, which is you're going to use the vector we identified here. So yeah, just grab the position with our point. So p and the neighbor. And then we want to say that if position.y is not equals to the position.y. So what does it mean? It means that we want to check only the points that are not on the same y. So we want to grab the attributes of the points that are not on the same y. So array attribute is a point, is a point 0, array point n, and stair attribute is point stair point n. Then we say if array attribute is equals to 1, so we're looking at those neighbors, and one of them is array point, or one of them is a stair point. Stair attribute is equal to 1. We say that we found that something is not allowing us to front extrude, and we don't extrude as well because we need our neighbors to be clean, so to say, as well. So, and then we say that if nothing was found, if found equals to 0, then we just say, yeah, extrude it to the front and multiply it by 0.2. So let's apply that, and you will see that our front one got extruded. Nice and clean. So let's revise what happened. So it was checking each point. So it was checking this point, and we saw, okay, this one is array point, no extrude front. It was checking this point. Okay, this actually is array point itself, so no. But this one, yeah, though it is its neighbor is array point, its neighbor is on the same Y position. So we were not checking that. However, the points on not Y position, they were clean. They didn't have any like ray point or star or anything. So that's why it was safe to extrude. And the same goes for these two. That is why all of this one got extruded to the front. So now we want to extrude the bottom as well. So let's say bottom extension. So in here, we want to say that if relative, oh yeah, for that we will need to grab the relative box first, sorry. We say that vector relative bbox is rel bbox 0 and p. So we want to know where it is, because we only want to extrude the bottom ones. We don't want to touch the top ones. So for that reason, we are using the relative bbox. So in here, we just say that if relative bbox dot y is not equal to 1 and touching roof, because if it touches something, we do not want to extrude down as well. So if touching roof is equals to 0, so those two have to be satisfactory. So it is not a top point and it doesn't touch anything. Then let's create a variable. It will hold our top neighbor, which we will find in our for each, because we need to know what top neighbor position is. We need to find, because it's how we're going to determine the vector direction where we need to extrude. Because once we extrude it down, we need to keep the angle of the roof. That is why we need to find our top point position. So for that reason, we are going to go through our neighbors. And we're going to say if position y is bigger than our p.y. So it is a top point. Indeed, we say that the top point is an n, and we just break because we don't want to run the for each again. And we say that vector direction is a normalized version of subtraction of our current position and the pos. So technically we don't actually need the top one anymore. So let me just do this. Yeah, that is actually going to be cleaner. So why are we going to use the pos? Because once we broke it, the last time our position was assigned with the correct thing. So this got stored. So now we can use it in here as well. So all we have to say is we want to move it on 0.25 multiplied by direction. Apply, accept. Ta-da! So what happened here? So it was checking this point and it was like looking, is it on top point? No. Does it touch anything? No. Okay, great. Now we are finding the top point and we are looking for the direction vector, which was this. And we are normalizing it, and then we're just moving it on 0.25 in the same direction that it already had with the top point. So that's what's happened. That is it. So all we have to do now is just merge it back with our sides. Sides, yeah, thank you. So what, oh yeah, we can delete the attributes we don't need anymore. So attribute delete. So we do not, we do not want the stir point. We don't want the touching roof anymore. So we go up, and now we grab this detail that we stored in our transform node, and we're going to put it back. And ta-da! All of our roofs are nicely extruded. Yes, that is exactly what we want. Beautiful. So that is it for the extension. Now let's delete the transform node. So now we can continue to the main loop. Next loop where we're going to create all the pivots. So let's grab a for each subnet. I'm going to create a get pivot. I'm going to color it. And we will need the extended version. In our loop, we will run it each number. For now, I'll make it run only once, so it's easier for us to debug and see what's happening. But we're going to use the same locate, so let's copy that. And from here, let's rename it to pivot. Actually, let's say a roof pivot. Pivots. And here as well. Roof pivots and roof pivots. Yes. So here we will need to locate. We also again do not want the sides, so blast the sides. We will say if side equals to 1. Yeah, delete it. Primitive. So let's call it delete sides. And here we're gonna have two big subnets. One will look for the like rims and all the decoration of the roof, and the other one will be like set dressing, which will include windows and chimneys. So for that, I will create a null right away. I will call it in. We're gonna collapse it, and we will call it rims. And I will create another one right away, so we remember about it. And it will be another subnet, and we will call it set dressing. And remember, you can always have more set dressing and other elements, because this is just an example to understand how I do the placement of certain things, but you always can make it much bigger. Because I think you can already see the pattern of what we're doing is just basically testing out the constraints and then finding the pivots. So let's dive into the rims. And one of the first things we have to deal in our rims is a very special case. So let me find you a seed which will illustrate it. So I found a seed with the case I was meaning to show you, and it's for me it's number 22. And as you can see, there's two roofs with the same roof direction. So I think this one is number 2. So let's grab that one. Yes. So what we want to do in the rims is we want to get the incoming roof of the same direction. So we will also need the other roofs. So let's go up, and we will grab, like this is a locate, and let's grab non-selected, I guess. So up, yep. So non-selected roofs. So non-selected, and we will plug it to the second input of the rims. So in here, and let's spin it so it does not give us wrong update. So here rims, and in we want to find the roof of the same direction. So what we're going to do now is we're going to bring a wrangle node, and we're going to find, say, incoming with same direction. So we plug our non-selected to the first input and our in to the second one. So let's bring it bigger. And here we will just comment find incoming prims with the same direction. Actually, not even prims, but roofs. So what we're going to do is we will create a variable like a boolean. So let's make it keep. We will also make an incoming list, because we need to know what are the incoming we are looking for. So we're going to grab it for a more primitive of 1, and it's called incoming and 0. And we also want to know the direction, so vector in direction. So we say that if length of incoming list is bigger than 0, so because we do not need to find anything if there is no incoming, right? So here we just say that we want to check the first one, incoming list 0. So if roof ID is equals to the incoming, we want to grab the direction, and we say that if the direction is the same, so absolute of direction, we will grab it from our primitive that we're checking, and if it's the same as absolute in direction, oops. So if they are the same direction, and we want to keep them, keep 1. And we just say that if keep was not updated, then we just remove it. 0 prim num, and we don't need the points. Apply, accept. Okay, so I have a mistype here. I already fixed that. Yeah, thank you very much. Well, lately it's been happening quite a bit when it doesn't update appropriately. So okay, so I think somewhere we deleted the attributes. So let's go up. I think we did it here. Yeah. So we want to know incoming. So let me check now. Yes, thank you very much. We still need those, and we want to also keep the direction. So the extension, yes. in the view, rims, and incoming. Still, oh, missed double equal, sorry about that. So yeah, so that is correct. That is our incoming of the same direction. So what we want from it, we want to grab the ray point. So what we want is a ray point equals 1. It's a point, delete node selected, and just thank you. That is the point. Usually it's the top point. And why do we want this ray point? Is because whenever we have this incoming roof here, we want to start our rim not from here but from here, because remember we have this like rims on the front. That is why we need to check for the incoming roof of the same direction. So ray point is here. We just want to move it a bit because if you remember, we extended our roof, so we want to kind of peak it. So let's bring in a peak, and we will move it on minus 0.2. Yeah, so it's perfectly sits where we extended, and 0.2 is because we extended our roof on 0.2, in case you're wondering. So the next thing we want to do is we want to get a sort, and we want to sort by y, and we want to reverse it, so 1 and 0 always on top. We also want to initialize attribute, so let's attribute create, and we will rename it to attrib init, and let's connect it. So what do we want? Well, we will want a name, point, primitive, so yeah, it's a point, and it's a string. We will also need to create normal number 2. You will see in a second why. It's a vector. We'll also need to create the up vector. Yep. And it's also a vector. And we also will need to create a scale vector. Scale. And it's also a vector. And we will put a default on 1, 1, 1, and everything 1, 1, 1. So yeah, attributes are initialized, and we are ready to bring a wrangle node. So attribute wrangle. So what do we want to connect is we want to connect this our main roof into the first input and our ray point into the second one. And let's bring it bigger. So which points we want to check? We want to check the top points. And this is easily now done because we sorted them. So if point number is more than 2. And we also want to exclude ray points. So we want to say that ray point is 0. So if that is true, we will want to grab a position. So p top is actually just can do it like this. And we also will need neighbors, p top neighbors, and our neighbors are 0 and pt num. We also need a bottom neighbors, but we will find them in a second. As well, we want to know the top neighbor, which we'll also find in a second. So first of all, we want to find bottom neighbors. So for each int neighbor, p top neighbors, we want to know their position, so point 0 p neighbor. And if p top 1, so technically I can just say p top y is bigger than pos y. So if our top position is bigger than the position we're checking, that means it's a bottom point, so we just append it. Bottom neighbors, and append our neighbor. And if not, that is our top neighbor. Very easy. So top nay is a nay. And we can have only one top neighbor, obviously, because we have only 2 top points. So after that is done, what we want to do is say that if there is a ray point from the incoming roof with the same direction, we want to replace the closest bottom neighbor with that point. Instead of starting from here, our rims and our pivots, because we're going to like resample the length, we will start from here. And we will ignore all this length from here. So that is why we are writing all this code. So let's say if there is a ray point from incoming roof of the same direction, replace the closest bot neighbor with that point, and start the rims from there. Yep. So say if endpoints of 1, so if there's any incoming roof at all, because if there's none, why bother? We will say that vector array point, and point 1, we want to grab the position 0, because there's always only one point. So we will also need to know vector and neighbor position 1. We need to grab 2 bottom points. We will say bot neighbor 0, and we'll just copy this line and neighbor post 2, and here is 1. And we also need to know the distance between the array point and those 2 neighbors. So float distance 1, distance array point post 1. We will copy that line 2 and 2. So let's see if any errors. Yes, we have some mistypes. Array point, it doesn't know what array point is. Oh yeah, we got at. Yeah, all correct. Cool. So now, what we want to say, we just literally want to find the closest one. So we say if distance 1 is smaller than distance 2, set point, point attribute 0p, we want to set the position of that neighbor to the array point. And we also want to say that it is no longer a array point, but it's a special point. It's a very special point. So here, array point, and we're not going to take it to 1 or 0, we're going to take it to -1. I just did it to not create a new attribute because it looks very cluttered when there are lots of attributes. So I just decided to use the same one. But you can create a new one for that special case. I just decided to reuse the array point. And in this case, absolutely the same, but different neighbors. So 1 and 1 here. Yeah. Apply and accept. So as you can see, it nicely moved up here. So maybe we'll create a new node where we'll sample the roof. It will start from here. So, and we'll just write it, and it's an incoming check. And so in here, we will start with our extensions, and for that we will need another attribute create. So attribute create, which we will call attribute variation. Yes, our extensions do have the variation. Because let me show you which variations we have. Chapters, your modules, and in here it's in the roofs, and we have 2 types of extension tips. So we have a tip like this, where it has this like nice a bit of decoration going on, and we also have the one without. And in this case we will have to use without because otherwise it will just intersect with our roof. Those are also used if the roofs are touching and so on. So that is why we need the variation, because right now we're going to use it, variation, and it's a string. Thank you. So let's bring a wrangle node. Let's color it, and we will call it front extensions. And let's bring it bigger. So in here again, the same gist. We want to say that PC num should be smaller than 2, and array point should be 0. Actually, sorry, we do not need the double, and we don't need a semicolon. So yeah, like yeah. So what we want to say is, again, same gist. We want to say that vector ptop is our position, and we want to say that ptop neighbors are the neighbors, and we also want to say that we want to know the bottom neighbors again, and we also want to know the top neighbor. And again, the same gist. I will actually even copy it from the previous one. I'll just copy it from here, find bottom neighbors, and we'll bring it here. So once we know that, we need to know our module size, like how long is our module. So I actually measured it, and the module I have is 1.5. We also need to know the normal. And it's a normalized version of p-top minus the point top neighbor. This for the correct orientation. So vector direction, we will need to know the direction as well as we need a new position. So let's create those right away. We will also need an integer for the new points we're going to create. And we also need to know the resample rate. So resample rates. So now we will create a for each loop for each of our bottom neighbor. It's technically just going to run twice. And in here is going to be a bit of calculation. So first of all, I want to find the module size. Module scale, I mean, sorry, not size, scale. So vector bottom position. So we want to know the position of our bottom neighbor. 0p and neighbor. And also we want to know the distance, so float distance. We want to know the distance between our bottom point and p-top and bottom position. And we also want to subtract minus 0.2. Why? Is because subtract 0.2 for the tip module, because my tip module that I created is exactly 0.2 length. So now we want to know the module amount. How many times do we have to resample? That is quite easy. We just divide distance by module size. And we have to also rent it. Extra bracket here. Yeah, we want to rent it. And we also want to convert it into an integer, so it doesn't give us a warning. And then we want to know the scale, because we can scale our modules. That's what we're going to do, scale y. And this is a distance divided by module amount in brackets. And that's we also need to divide it by module size. Yeah.
I hope those explanations were not too confusing for you, but if they were, no worries, I'm here to explain it in greater detail. So let's imagine that this is our distance that we have to cover with our modules. And for the sake of an example, let's imagine that it is 4.2. And let's say we have modules. Let's say that this arrow is our module, so module, and it is 1.5. And if we try to fit this module into our distance, we will be able to put first module, so module 1.5. Then I put a second module, 1.5. But look, the distance that is left, so it is 4.2 minus 1.5 multiplied twice because we put two modules, and it is 1.2. And 1.2 is smaller than 1.5. So if we put a module there, it will exceed our distance. And that is not what we want. We want our modules to fit perfectly into our distance. So what can we do? Well, the first thing we can do is ask ourselves, how many times can we actually fit a module into this distance? And the answer for that is, we'll take our distance and we will divide it by our module. And then, since we don't want an even number, we want an integer, we will rent it. And what we will get is rent of 4.2 divided by 1.5. So we get rent out of 2.8. And this is, and I will choose a new color, let's say pink. Yeah, that's better. And it is 3. So 3 is a magical number. 3 is an amount of times we can fit a module, but not this size of module anymore. It is a new size. So what is that size? Well, to get that size, we have to take our distance and divide it by that new size. And we will get is 4.2 divided by 3, which is, and let me choose yet another color, let's say this green, and this is 1.4. So 1.4 is a new magical size that if we take our module of that size and we put it 3 times into our distance, so if we put this 3 times, it will fit perfectly. And that is exactly what we want. However, our module is not that size. So what is that size? Well, it is something multiplied on our module size. So I need another color again. Yellow. Yes. Multiplied by scale. And that is our size. So that means that our scale is 1.4 divided by 1.5. And what that means, if we replace all these numbers that we have with variables that we have in our code, we will get, and let me hide this so we have space to write. So what we will get is, we will get that our scale is, and we have to track all the way back. So what is 1.4? Well, 1.4 is it distance divided by, and 3 is rent of our distance divided by module. So that is 1.4. So let me show you that. So that is 1.4. And then we divide it. And what is 1.5? Well, 1.5 is easy. 1.5 is our module. And since our 3 in our code is module amount, and 1.4 is our size, we will get that it is distance divided by module amount and divided by our module size. So hopefully this gives you a better insight on the calculations we are doing, and you have a better understanding of what is happening when we are scaling our modules.
So now we're going to set up axis for copy node. So it's a dir normalize, and we're going to just subtract ptop from our neighbor. Yeah. And now we're going to check if bottom is array point, int array point bottom. Remember that special case that we created, so we're going to check for that. So set up the scale now. So vector scale. Forgot semicolon. And here we're just going to set the normal. So it's a cross of our normal and up axis. And now this is like very tricky because what we're going to do now is very eloquent. So what we want to do is we want to invert our modules because we have like two sides, this one and this one, and they have to be inverted. Like you literally have to invert the modules for each side, and we need to know which side is which. That is why we're gonna have this cross right now, and we want to like check if we're gonna make it with a dot product direction and the normal. We want to get a cosinus because we want to know the angle between them. And cosinus returns you radians, but for the convenience, let's convert it to degrees. And if it is bigger than 90, we want to set scale to be 1, scale y, and 1. Sorry, scale y. However, in other case, we want to invert it. Else, we want this scale to be inverted. Scale, yeah, and we wanted to make it minus here. Apply. And some typos, expecting, it's 35. 35. Really? Oh yeah, here. Apply. So yeah, so now after we set up the scale, we want to resample it. Resample if needed. So we want to append, first of all, to the resample rate module amount. So for int x0, and it will go as long as we have the module amount, so x++. So new position. We will now find a position for the new point, which we're going to be resampled. So point 0p neighbor, because remember we're still running for every bottom neighbor, is plus direction multiplied by scale y, multiplied by module size, multiplied by x, plus the direction multiplied by 0.2, and again, this is the tip thing. So new point is just added to that new position. And now we're going to set all the parameters for it. So set point attributes. So we're going to set its up, new point, and it's going to be at the direction. Set. Just going to copy that because it's going to be quite a bit of attributes. We will set its normal, which is just normal. We're going to set its scale. And the scale is a scale. We're going to set its keep. And we're going to set it to 1. And the name. And the name is going to be front extension. Front extension, yes. And then says that if x is equals to 0, so it is first point. We want to also add a new point. We want to add the tip. So whenever it begins, we will add a tip, and after that, no more tips. So we will add this point to the new position. We'll create a new vector, new scale, and set scale.x 1 and scale.z, because we want to keep it unscaled in y, so the length is always the same. And now again, ton of set point attributes, so we will also set its up, and yeah, again for the new point. And we also will set up, technically you can just copy all of this, so let's do that. And but a standard front extension, we want the front extension tip, and we also want to set its variation. So let me copy this one, grab it here, and variation, and the variation is 0.1 at first. However, we want to check if bottom is a ray point. So if it's a special case where we identified ray point as -1, if you remember just now, then we want to set its variation to something else, which is 0.2. Apply, accept, bam. Nicely done. That is our pivots right here, these ones. And I also want to see if we have the keep attribute actually created for us, because I'm not sure if I actually created that. No, I don't think we actually have a keep attribute. No, we don't. So in attribute initialize right here, create a new one. We will call it keep. It's a point integer, because in the end we only want to keep the pivots that we created, and we will just delete all the unnecessary geometry. So let's check again. Yeah, awesome. That is our front extensions. Now it is time to make our top rails. Now it is time to make our top rails. We want to keep only the top points, so let's blast. Yeah, there are many ways how to do it. I'm just going to use the bbox. I'm just going to say that p.y is the same as bbox op input path of dy maximum. Apply, accept. Yes, so 2 here, and we're just gonna call what you don't like. It's not a valid group, but you're working. Not a valid group. It's very strange, but it's working. So we want to rename it to top. And we also want to get the ray points. So it's going to be our ray points. Ray points. If ray points is equals to 1, we want to keep that. Sorry, a ray point. So yeah, we do have a ray point. Yeah. Now we will grab a new wrinkle node. We will color it. dark blue shade, yeah. And we will call it a rooftop rail. And here, let's make it bigger. So, what we want here? Well, first of all, we want to check whether we have any waypoints. So check if if there are any waypoints. So we will need two vectors for that, p1 and p2. And you say if point 0 waypoint 0 equals to 1. It's just a matter of assigning p1 and p2, because we always want p1 to be the waypoint. So point 0, p and 0. And we also want to grab this one and get it a 1. And else, and it's a 2. And else is just the reverse order. So now, based on the amount of the waypoints in the roof, we want to recalculate the distance. So float, let's actually write it down. Based on the amount of waypoints in the roof, recalculate the distance. So float distance is distance between p1 and p2 minus 0.4 minus 0.2 multiplied by the number of points in our waypoint. So if there is any waypoint, if there is no waypoints, nothing's going to be subtracted. Oops, it's a minus here. 0.4 will be subtracted. However, if there are 2 points, both the points are waypoints, we will not subtract anything. So next thing is the module size, and because since I made them, I know the module size is 2. We want to know the module amount. That is why we're gonna recalculate. And why are we doing, by the way, this? Let me explain. Because let me just apply accept. It's because whenever we end the waypoint, we just end in a rail. However, we also have a rail tip. So here you are. That's a rail tip. And as you can see, it also takes kind of a space from the rail. And I calculated the distance. That is why it has to be 0, like this is 0.2. And it kind of takes space from the rail. However, if it is a waypoint, we don't need this tip. Therefore, this space will be occupied by the rail itself. So let's go back. And again, int module amount. It's a distance divided by module size. And let's convert it into the integer. We also need to know the scale in z. So it will be distance divided by module amount. And all of that is also divided by module size, so the same as our extension. Size and vector scale is set to 1, 1 and scale z. So now we can resample. So vector direction, it's kind of absolutely the same approach as we had for the extension of the roof. So normalize p2 minus p1. We also want to grab the new position, and we will need a variable to hold our new points. And we just say for int x 0 and x goes as long as the module amount and x plus plus. And if endpoints 1 is equals to 0, so there are no waypoints whatsoever, we will need a new position. Is simply p1 plus the direction plus the scale z, multiplied by scale z, multiplied by module size, and multiplied by the x, and plus the direction multiplied by 0.2. So, and that's what we're gonna say. We say if no waypoints, then move the roof 1 tip step. However, in other case, we do not need to move it. So new position, and we just keep it at this. So then we're just gonna get a new point. It's add point, and we add it to the new position we just created in our loop. And again, a lot of assigning of attributes. Set point, attribute, new point, and the direction, and set. We want the up vector. In this case, it's very easy. Up vector is just literally up because we don't want anything fancy. It just rests on top of the roof. So another one we want is a scale. And scale is scale. Yeah, that is the one we set earlier. Another one is keep. We do want to keep these points. And the name. The name is top rail. So apply, and some mistypes, variable z, 31, module size, oh yeah, should be multiplied by x, sorry. Still some mistakes, x here, apply, yeah, awesome. So once that is done, we want to delete array points, so vector normal for int x equals 0, x smaller than n points of 0, so for every point in the first index, plus plus, if point 0 array point of the x is equals to 1, we want to remove it. 0 and x. However, if it is not the case, if it is not array point, you want to get its normal, and that is for the roof tips, by the way. And when we set point attribute 0 p, we want to minus normal, multiply by 0.2, because we need to move the pivot a bit. I will even comment it out. Move the point for 0.2 for the tip, for the tip, and set point attribute. Another thing we want to say is name. We forgot to say it's an x point here, so x, and it's a top, not drop, top rail tip, and set. So now, what's the warning? Implicit cast from float to integer, 18 from float to integer. Oh, you want us to, you want me to rint? Yeah, you just wanted me to rint. Okay, so, as you can see, we got these points. This is our tip point, if I'm not mistaken. Let's see, 0, 0, 0, 0, 0, 2, name. Yeah, it's a top rail tip. And we got top rail twice. So I found out, don't forget to put it on detail only once. So sorry about that. We don't need to run for every point. We need to run it only once. So once that is done, we can now merge our front extension and top rail. So once that is done, don't forget to blast our keep. So keep equals to 1. Delete non-selected points. So those are pivots. So what we also want to do is we want to initialize the attributes. So let's create a wrangle. So attribute initialize, and here we want to say that first of all the type is roof, Also, if there is no variation, is like empty, you want to make sure that it is 1. So for now, that is it. We will add more later, and let's place the modules. Let's see what we have. So I'll just go up and I'll just copy it from the other ones. So let's say from set dressing. And it says it cannot find certain things, so it doesn't know where the roof front extension 0.1 is. Huh. Let me see. A roof. How was it called? A roof front extension 0.1. It should know where it is. Modules. So. Oh yeah. Sorry, I had a crash. That's why it cannot find it. So let me just resave my file. So now it should be able to find it. Yes, all correct. So as you can see, nicely placed. And let me merge it with the roof so you can, oops, you can see it nicely together with everything. So, so yeah. Oh, we need the extended version. Not the, did it? Yeah, this one. And so what happened here? Oh yeah, we need the technically we actually should get it out of here and get it here. And we also need to disconnect this and plug this in here. So yeah, as you can see, nicely works. And we also have the pivots for 0 and 2. Let's place pivots everywhere. And just want to make it end frames of input path. So as you can see, everything is nicely placed. And our tips are only where we need them, so here are no tips. So yeah, nice. So that's it for this video. In the next one, we will continue placing the set dressing elements, and I'll see you then.
Hello and welcome back. In this episode, we will continue on with roof set dressing. And you might notice that the sound is a bit different. That's because I borrowed a new microphone. Yay! So hopefully the sound will be a bit better. And yeah, let's just continue. So we stopped in the roof modules. We have our get pivots. So actually let's color it in a bit darker shade. Yeah, that's good. And let's decrease our number range to 0. So we're working only with one case. And I cut out the expression we have here and I will put it in the transform node so I don't have to rewrite it when we want to see all the cases. So let's dive into get pivots. So in here we already have the set dressing network. That's good. So let's dive into it. So in here our null, let's rename it into n. And I will actually create a subnet right away. It's a subnet called Windows. We will have 2 subnets for the set dressing, but for now we just need the Windows. So let's dive into it. Here's our n. And the first thing we want to do is we want to modify our normals. But before we do that, let me enable the point numbers. We want to sort our points. So actually let's go up and in here, let's grab a sort because we will use it for both of our subnets. And in here, we want to sort by Y and reverse. So why do we do that? Because we want to make sure that the top points are always labeled 0 and 1. And now you will see why I want to do that. So let's go back into Windows, and here we will grab a wrangle node. let's call it normal. And here, make sure it runs over points. Let's make it bigger. And in here, we will make an if statement that we want the pt_num to be bigger than 1. So well, that's why we sorted, because we don't want to check the position all the time or check the relative bounding box. We just want to check the point number. And this way we ensure that we always run only on the bottom points. That is what we want. And what we want to do now is we want to make sure that the normals of all the bottom points, they continue the edge from the point we're currently running over to its top neighbor. So let's do that. So for that, we will need to grab the neighbors. So neighbors, 0 index input from the point we're currently running over. We want to run for each of its neighbors. So int n in neighbors. We will need to grab the position of our neighbors. So we will need to have a vector pos, which is identified inside of the loop. And it is a point. 0 index, we want to grab its position of the neighbor. And we say that if our current position in y is smaller than the position we just grabbed from our neighbor, then our neighbor is the endpoint. So let me create an identified integer called name. And once we identify that, we want to just break the loop, because we do not need to run multiple times. We always know that the point has only one top neighbor. So now we can make the normals. So normals is a normalized version of subtraction from our current position to the position. And why I'm just having this position? Because the last time we identified it with n, which is our neighbor, and then the loop was broken and the position wasn't assigned a new value after that. So our position is still holding the value which is true for the neighbor. That is why our position, we can just use position. So apply, and as you can see, all of our normals are now pointing into the same direction as the edge that holds this point and its top neighbor. However, let me apply an except. If we look at the other case, so which is, let me see, I think it's number 2 if I'm not mistaken. Yes, it is. So here, one of our points was moved, one of the top points, to merge with another roof. So the edge direction was modified. And we do not want that, because this normal will be a driver for later positioning, and it has to represent the elevation of the roof. So the direction has to be as if its top neighbor was never moved. So how are we going to achieve that? And let me actually color the window, the subnet, while I see that. So let's go inside the subnet and back to our normal. So how are we going to achieve that? Well, first of all, we need to know, was the top point moved or not? And it is quite simple, because we have the ray point attribute, which is an integer if I'm not mistaken. Let us see, yeah, it is an integer. So we will grab that. We want to know if ray point name, so if our neighbor is actually a ray point. So we're going to grab its ray point attribute. And we're going to grab again from the same neighbor point, we're going to grab the normal. So you might want to say that if it is a ray point, so if ray point neighbor is 1, so if we check in, for example, this point and we check its top neighbor and we see, yes, it is indeed, it is a ray point, because it has a attribute of ray point equals to 1. We want to check 2 things. We want to know what direction it's pointing, because based on that direction, we will zero out the value in that axis. So for example, if our normal is pointing in Z, and it doesn't matter whether it's positive or negative, we want to make sure that our normal does not have any value in that axis. So let me demonstrate. So if, and we say our direction neighbor dot x is not 0, so it has some value. Oops. It has some value in that axis. We want to say that n, our normal of the point we're checking currently, is 0 in that axis. So 0 in x, but we will keep all the other axes intact. And we want to check the same. So else if direction neighbor dot z is not equals to 0, we want to zero out that axis. Yes, so apply, and as you can see, our normal is now parallel to its another bottom neighbor, which is exactly what we want. So before we close our normal, we want to add another attribute, which is a roof distance, and this is an attribute we will need later on. So we want to know the distance between our current point and its top neighbor. So pause, so apply and accept. So that is all nice and well, but again, I will show you another thing that might happen. Oops, I wanted to say up. So up, up. So now, yeah, thing I'm going to show you because I don't remember which number of roof it is. But if we paste all of our roofs, well, actually here I do not see that happening. Oh yeah, I see that happening. Yeah, this nasty little thing, which you might not notice immediately, especially if you're running something custom of your own. So let's figure out what's happening in that roof. I think it's number 1, if I'm not mistaken. Let's see. Yeah, it is number 1. So let's go back and back and back. So what's happening? Why is this normal pointing into a very weird direction, which is not true, which is not correct? So the answer lies in their position. So if we check point number 5 and we check its position in y, it's 2.8393, and point number 2 is very similar, but not exactly the same. And well, we could read, like, for us it doesn't matter, but for Houdini those numbers are different. So this becomes invalid because it is, for example, this point, it is higher than this one by a very, very tiny bit, but it is. And it might happen more than only in this case. Sometimes it can be such a small number that it's just, we would neglect it, but Houdini wouldn't. So we need to tell Houdini that it should neglect those kind of numbers. So what we say is we rind the positions. So only if they're different by even numbers, we want to actually account for them. And now that I'm thinking, if we round it, sometimes maybe if our roof is actually much smaller. So let's do it a bit different. So we want to multiply it by 10 and divide it by 10. So we round it to the, so apply and set. So now it will work as well, but what I did is instead of rounding it to an even number, I'm rounding it to the next number after the comma. So if we had something like this, that would become, well, it would, because we multiplied it by 10, so it became 8.7 and something, which became 9. So let me actually 6, 7, 6, 6, 8. That's what it became, which becomes 9, and then we divide it, which becomes 0.9. So we rounded to the next integer after the comma. So yeah. So apply and accept. That's all good. So the next step is we want to isolate our bottom points. So let's grab the last node, connect it, and we want to delete 0 and 1 because, as you remember, we sorted them, which makes our life much easier. So we want to say that delete points, and we will call it bottom. And the next step is we want to sort them. And the way we're going to sort them is we want to sort them perpendicular to the direction of its top edge. And we're just going to grab the point numbers 0 or 1. It really doesn't matter because we do not care whether it's a positive or negative direction. And in sort, we're going to say that we want to sort by vector. And to make it perpendicular, we're just gonna input. So I'm saying so I want to tell it to go to the normal. And I want to grab 0 point. I want to look at its normal, and I want to grab the z, not the x, z. And I will input into x. And the same I will do with z, but I will input the x. So this way, it makes sure that it is perpendicular. So, and please be aware, this only works because we only have 2 cases of the normals. They either lie exactly in z or exactly in x. If you would have another kind of normal, that wouldn't work, so just beware. So, after we sort it, we want to resample our points. We want to convert these points into something we can work with, because currently these points do not represent anything but the corner of the roof, which is not what we want. So, let me actually grab another case, which is a bit longer. I think it's number 0. So we have more points and you can see better. Yes, it's quite long. Good. So here, let's grab a wrangle node. And now you will see why we sorted the points. So let's call it resample. We want to make sure it runs over points. That's correct. Let's make it bigger. So here, we want to make another condition, and that is why we sorted the points, because now we always know where the edge starts, because this is previously was the edges of our roofs, and now we always know that the edge starts at 0 and at 2. So that's what we're going to write. We're going to write if ptnum is equals 0 or ptnum is equals to 2, that's when we're going to run our resample. And we're going to resample to its neighbor, which we also know because its neighbor, it's just ptnum plus 1. So we made our life much easier by just sorting the points, and we will never have any other number than 4 in our roof, so we can afford ourselves to rely on the point numbers. So we want to also grab the neighbor position. Neighbor position point 0 index p and neighbor. Yes. So now we want to grab distances and scales and all the jazz. So let's just comment it out. We will call it distance and scale. So first things first, float distance. And you might ask yourself, why are we putting a float distance and not an integer? Because, well, our roofs are always constrained to our modular grid. But then you're forgetting our very special case of closed balcony when we have half a module. So sometimes our distance might not be a whole number. That is why we will put a float. So it's from the LP to our neighboring pos. So the next thing you want to identify is a module size, which we know is 2. And it's not the size of the window, beware. It's the size of the segment where the window will be placed, because the window needs this kind of segment. So that is why our module size is 2. Another thing is we want to know the module amount. How many times do we want to resample? And as you might remember, it's an integer of the rounded division of distance and module size. So next thing is you want to know the scale in Z, because sometimes we might want to scale our window. So that is distance divided by module amount in brackets, and we divide by module size. And as you might notice that this sometimes might be equal to module amount. So in most cases, our scale Z will stay 1. But in our closed balcony case, we might need to scale it up. That is why we need this. Because if we didn't have that case, we could have just deleted it because it would always be equal to 1. But not in that case. That is why we need it. So now we are ready to resample. So let's grab a direction in which we want to resample, which is a normalized version of our neighboring position minus position of the current point. We will need to grab a couple of variables that we will identify in the loop, such as new position and the new point, because we will create new points. And let's write the loop. So int x equals 0. X is smaller than module amount because we want to run as many times, but smaller by 1 because we don't want to run to the last point, and you will see why. So the new position. So what is a new position? Well, we have our reference, which is the starting position, our current point. We will move in the direction. So we will move as many times as the module size, like the distance. But sometimes it might be scaled, so we will multiply it by scale. And we will also multiply it by the step. And then, because I will actually show you, because if we keep it like this, so new point is at point 0, new position, and let's remove all the unnecessary points right away. So remove point 0 PT now, so I can show you. So if we do that, yeah, we're not grabbing the last point. So if I would do this, and I want to show you, so I will blast 0 and 1, and I will add by group, and I will resample by our module size, which is 2. This is what we have now. So, and we're not making the last point, of course, but that is not what we want, because if we place our windows there, so if we place the windows, copy, and I will grab file, window. We only have one window, but of course you're free to create more variations. So yeah, we do not want to copy to the, yeah, thank you. So we might actually grab the other one, and I want you to see the roof. So as you can see, it just doesn't make sense, because our window has a center bottom point, and it just doesn't make sense why it is on the corner of the roof. So that is why in our resampled version, we want the middle, not the corners. So how are we going to achieve that? Well, that is why we don't have the last point, because we're going to offset all these points by half of this section. And we already know the distance of this section. Here it is. That is a section. So let's just copy that. And we will divide it by 2, because we only want the half. Apply. And ta-da! So now if you place these points in here, that makes much more sense. Still not perfect. We have lots of things to go through, but I mean, that's better. You can't deny that. So let's delete all these unnecessary nodes. You might notice that, yeah, we don't have any normals or anything anymore. So let's actually bring back all the attributes. But by all, I mean only one. 0. So we want the normal to our new point from our current normal, and we want to set it. Apply, and why are you complaining? Oh yeah, set point attribute. Apply and accept. So now we have our normals back. Yay! But before we do that, we want to contract our points in the axis that is parallel to the roof edge, the top roof edge. So how are you going to do that? Yeah, we can kind of do this sort and everything, and then make a transform at this constraint, but let's make our life a bit easier. Let's just grab attribute transfer. Let's transfer the normals from our in, where we have these normals. And they nicely distributed along our roof. And what we want to do now is we want to grab a pick, and we just want to pick them a bit. I think it was 0.06 if I'm not mistaken. As you can see, they contracted in that axis. And now we just want to attribute transfer everything back. And here we only want the normal, as well as here we only want the normal. And yeah, we have everything back. So voila, very simple trick. So now we want to grab all these nodes, and I want to make a subnet out of them, because they occupy a lot of space and it will look very noisy if we keep working in such environment. So we will create it, or we will name it resample. And now we can create our main wrangle. And now we can create our main wrangle. which we will call Windows address. And so what we're going to do in this one is we're going to make sure that only valid points can exist, because right now, if I go up and up again, and I will grab this non-selected, and actually let's connect it to the second input, and here again, connect it to the second input. And here, let's grab a null, call it in. We have lots of cases that just cannot exist, like this point. It does not make sense. Why would anyone in their sound mind build a window that wouldn't see anything else, like it wouldn't see the streets or nature or anything, would just look inside of another room? That just does not make much sense. So that's what we're going to check now. So in this in, let's plug it into the second input of our wrangle. And before we do that, we want to make another attribute. So let's go inside of resample. And in here, before we resample, let me move everything a bit, we want to create an attribute, which we will call scale. Because we want to know, have we scaled the module or not? So it's going to be a vector, yes. And in resample, we want to set point attribute. So let's copy this. We want to set the scale, and we want to make the scale. So let's make a vector scale, and we will set it. So we will say scale in Z. And yeah, it does not make sense because we're putting it in X, but our window is oriented a bit different. So if you look at the module, you will see why. And yeah, we want everything just one. So in scale, yeah, we want not to put the normal, but we want to put the scale we just created. So apply and accept. Let's display the last node, go up. So now, spreadsheet, points, oh, that's vertices points. Yeah, you see that our scale is actually slightly bigger than 1. So that's how we scaled it a bit. So that's good, good and sound. So now in our Windows address, make sure it runs over points, important. Let's write our Windows address. So we will need a probability because we want it to be randomly assigned, which out of the remaining windows can actually exist because we don't want all of them to be spawned. So after we have the probability apply, let's create handle for it. Yes. So now we want to write the constraints. Well, first of all, do not even check if it doesn't satisfy our probability. So to make it random for every point, I will just make it random per its position, because if we make it random per its point number, it will have the same kind of pattern throughout every window. And then you can also add a PT num. It should be smaller than our probability. And it is why we also needed a scale. We do not want the window to be spawned if our scale X, or previously known as scale Z in our sample, is smaller than 0.9. Because it is smaller, so we don't want to scale window that much. So we just say that, sorry, but that's not a window we want. Apply and accept. Well, no, not accept yet. But I want to make sure the probability is 1, so all of our points are kept. Because right now, if you see that probability, oh yeah, we don't remove the points yet. I was like, why does the probability work? But yeah, we want to make it 1, so all of our points are kept that actually can exist. So here, the first thing we want to do is, and actually, I will close the window again because I want to show you one thing. And let me grab a null. So if we copy on the current points our window, and yeah, forget about the orientation. It's not correct yet. So you see that the windows are on the very bottom of our roof, which does not make sense because you always have a bit of an offset from the very corner of the roof. And this offset also depends on how tall the roof is, because the taller the roof is, the higher the windows are placed. So we want to make sure that this is accounted for. So in here, we want to move them. So we will subtract from our position, and why subtract is because we're gonna move along the axis but in the negative direction. And why along the axis? It's because our axes are perfect for this, as they are the continuation of the angle of the roof. So if we move these points along the axis, they are perfectly moving along the roof as well. So we will say that normal, and first of all, we always want to move it just a tiny bit by 0.15. So apply. Yes, see? And actually, I want to demonstrate you. I want to prove that it will move along the roof. So I will grab a peak. Not this. This, yes. Thank you. And see, it perfectly stays on the roof. There. My point is proven. You can't argue with it anymore. So yes. So we will move our position. So, yeah, that is correct. So, but for some reason it didn't move anything, which is interesting. So, from the point, we're running over the points. Our probability is 1, and our scale is, oh yeah, it has to be bigger. I mean, like, wow, I'm just, mistype, apply and accept. So, yeah, as you can see, all of our points have moved. And now if you lower the probability, you see that some of them do not move anymore. So yeah. But as I mentioned, if the roof is bigger, so the windows should be higher. So how are we going to do that? So we will add another normal, and we will multiply it by the roof distance. Remember, we made this attribute in our normals. Now it's time to use it, but we just don't want the roof distance only, because then the number will be really, really huge. So what we want to do is we want to have a power of 2, and again, it will be very huge, but we will divide it by 4. So it is always, in most cases, it will be smaller than 1, that's for sure. And if you power it, it will be even smaller. So only if the roof is really, really tall, then it will be proportionally taller the window as well. So that's just the number tweaking I did, and I found that works. So apply and accept. So we have that in place. So now, actually, let's go back, because that's not, of course, that's not all. That would be too simple, right? And now we want to modify the normals. So the normals are the same, kind of, but we do not want it anymore to represent the angle, because why did we have this, the value in y? That's because we wanted to represent the angle, but now we do not want it anymore. We don't need it, and it won't place our windows correctly. So we will zero it out. So 0 in y, but everything else we will keep intact. But now it's not normalized anymore. So let's normalize it. And another attribute we will create immediately is the name. It's a window. Window, yes. And the scale is 111. It might be modified later on, if I'm not mistaken. Yes, it should. Yeah, it will. So, and now we will run all the checks to make sure that these points have the right to exist. So I will do the check for the other. I will even for the non-selected roof's intersection, because we're gonna check for its intersection. So we will need our favorite and beloved PV and UVV, and we will grab integer intersect equals to our intersect function, and we'll grab from the first index input, and we will run it from the current position, but slightly offset, otherwise, well, it shouldn't actually coincide with our own roof, but just to make sure. Yeah, what am I doing? Oh yeah, multiplying it by 0.001. And we want to run it as long as 10 units of our normals in that direction, and just insert our PV and UVV. So if intersect is not true, which means it's true, this point cannot exist, because it intersects with some of the roof. So in front of it, it sees a roof, and it does not make sense why the window would be there. So apply. And as you can see, many points disappeared. That's because Yes, all the correct points they disappeared because in front of them they saw a roof and they were like, well, I don't have a reason to exist. So they were deleted. And now we want to make another check, and I will actually demonstrate you why, because, well, it seems like everything is nice and well and that's perfect, right? But not exactly. I'm not sure if it will show you in this case, but I hope I can prove you my point. So window. Now we can use actually the normals because now they are nicely placed. We will merge them with our roof, which is here. Okay, in this case, this is nice, but is it true for every roof? Let me check. Let me grab a transform node, copy this, place it in here, and let's see. Well, this one is freaking out. We will need to check what's happening there. But yeah, that's what I'm talking about here. This window doesn't have any shame in it, and it just does not continue to the end of the roof, which is like outrageous, right? But we can tell it to do so. So, well, let's go back to our 0 case, though it is fine, but we'll write for that. So we do not need all these merges and such, but I will keep it for now just to prove you that it works. And here we want to check for the distance till the roof. So we want to know from the tip of our window to the roof, what is the distance? So we want to know the vector of window tip is our current position. And window tip, tip in Y, because our tip is higher than our pivot, because I can show you file. Window. So that is our pivot, the point we have, this position. And in Y we need to add number to have this point. And since I measured this module, I know that it's 127. So if you're working with another artist, make sure you communicate this kind of values, because if they change, the system breaks, and yeah, not pretty. But of course you can make a check or by bounding box. That's also possible. So once you load the modules, the system can automatically know all the dimensions, which would be awesome. So apply. And we go back to our Windows address. Now it complains because we have somewhere window. Yeah, so now it shouldn't complain. Yes. So now we want to run a second intersect. So intersect 2, intersect, again with our first index input from our window tip for this time. We want to run it minus in our normal, because we just raised this once. I want to point it into the roof. And I just realized we do not have actually the roof itself, which is a bit of a problem. So let me finish this line so it does not complain. PV and UV. Yes, we're using the same ones because we do not care. So I apply and accept because we don't actually have the roof here. So yeah, so in we actually should have all of our roofs. So we would have to have each. So now if we go back into, yes, that's what we want. And now, yes, I knew I didn't put it for nothing. We really need this because otherwise it will coincide with our own roof. So, and why are we putting 2? Because again, I measured the window and its depth is 2. So if the distance is bigger than that number, that means we have a problem. The window will not reach the roof. So we want to say that if intersect 2 is -1, so nothing was intersected. Or, and I forgot one thing, that or thing, we want to grab the distance. We want to know the distance from that. Because right now we need to know what is the distance from our window tip to the roof. So float distance is distance, and this time we actually need our PV. So we want to know the distance from window tip to our PV, and PV represents the point where the intersection happened. It holds the position. So we want to know the distance, and if the distance is 0, I mean, that just does not make sense, right? That's why we want to remove the point. Remove point. We need not to forget to modify our scale. I almost forgot about that. So our scale will now become set, well, 1 and 1 as it was, and in Z it will become a distance, because that's how much we need to modify it to fit perfectly to our roof. So apply the set, and now, as you can see, it's scaled, because if I do not do that, if I comment it out, oops, that's what it does. But because we now have this distance, it knows exactly how much it has to scale to make sure that this point sits on the roof. How awesome is that? So if you go up and up and up, and we look at that roof again, which didn't have its windows reaching, now it should. And yeah, I really need to check what's happening there, but yeah, see, it scaled it, so now it always sits on the roof. And what's happening here? Let me check. So, oh yeah, well, it's, by the way, it's roof number 3, and I was checking why it's not working. It's because we haven't finished our code. Yeah, so there's else, because if this is not satisfied, because it didn't modify our points at all, because this wasn't satisfied, we want to make sure to say else, and we say else, and we want to just remove the point, because it didn't satisfy to our needs. I mean, no hard feelings. But yeah, because this roof is too narrow and it wouldn't fit 2 windows, it wouldn't look nice. So, and let me delete all the unnecessary notes. That is our windows, by the way. I mean, that's it. We have them, yay. So that means a null here. Let's go up and up and up. And then here, if I let it run for all the roofs. Oh yeah, we're not going to see anything because I just deleted them. But, oops, but yeah. That's all the points that are possible to exist. And if you modify the probability, let's spin this view, and let's say something, but not too high, but not too small, 0.6. And as you can see, we have some of them just disappeared because, well, that's life. But no, because that didn't satisfy to our probability. So yeah, oops. That is our windows. Let's actually merge them together with our rings. Now, so the points attribute initialize, and now up, we should be able to place our modules. And looks like a Christmas tree, right? But yeah, that is nicely placed our windows. And this one is very small, though it should be a bit taller. I think that's the reason, because something happened to our roof distance attribute. So let's unpin the view. Let's again zero it out. Go back to our set dressing and let's check resample. Roof distance all 0. Yes, that's incorrect. So let's see, in resample here we have a roof distance is again 0. And our roof distance here, it's fine. So what happens? Roof distance here. Oh yeah, in our resample, we did not get the roof distance here. So what we want to do is we want to set a new attribute. And we want to say that roof distance is the roof distance. Let's apply and accept. So now in here, yes, that's what we want to see. Marvelous. So now our points should behave properly. So let's check here, and let's get a number of primitives expression, put it in number range. Yes, I already see this point moved. So I think that's correct. So let's place our modules. And yes, you can see that now it works and behaves correctly. So that's it for our windows. And in the next video, we will continue on to the chimneys. And I'll see you then. Thank you for watching. Welcome back. In this video, we will continue with our roof set dressing. And now we're gonna place chimneys. So first of all, let's decrease our number range to 0 again, so we are working only with one case. Let's dive into our Get Pivots network. And inside of set dressing, we will create a new subnet, which we will connect to the sort. We will call it N. Create this subnet, which we will call chimneys. Color it in the same color as our Windows network, and let's dive into it. So that's our in. So first of all, to create a range of points, we will just grab a scatter node. And in total count, 100 is more than enough. And that is already the foundation for our random points for our chimneys. However, there are cases which cannot exist. What are those cases? Well, first of all, our chimneys cannot spawn very close to the edges because then our module will stick out and plus it will look weird. As well as, if we go up, we have our Windows points. And chimneys shouldn't spawn on the same location as our windows because then they will overlap, which also will result in a weird look. So, knowing that, how are we going to constrain everything? Well, again, we will need a wrangle node. We will connect our scatter points. We will name it pCloud, and that's already a hint how we're going to do it. Yes, we're going to use point cloud and PCFind functions to avoid cases we do not want. So it's easy with our windows because all we need is just connect our windows. So input number 2. So that is already our points. But what about the edges? How are we going to account for edges? Well, that is very simple as well. Just grab a resample node. And we have points that represent our edges. Very simple. And we will plug it into the wrangle node as well. So inside of the wrangle node, let's make it bigger and start coding. So first of all, let's initialize some variables. So as name for string attribute is chimney. Scale is 111. You can make it a bit random as well in Y if you'd like. That will make the height of the chimneys a bit different. We will also need a probability, so float probability, and we will create a channel for that. Probability. Did I spell it correctly? Probability, yes. And we also will need an important thing, which is a bounding box, and you will see in a second why we would need it. We would need a bounding box in Y. So we'll call it base BBY. So let's connect those. So we have these two channels and base BBY. And in here, what we want to do is we want to grab a bounding box of input path of the first index. I mean, 0 index, but first input. And we want to know its dy maximum. So why do we need that? That's because we don't want our chimneys to spawn on the very bottom of our roof. So I will show you. So what we want to do is limit our range in Y, and it should always be bigger than our bounding box minus 2. So if that is true, we will say continue, continue, and else we would say, oops, remove that point, and you will see that it will create kind of a division of points. So and it does not know what continues, then it's just a pass or not. Doesn't know the pass, neither doesn't it knows continue. Something of nothing. Okay, apply, and then we have an identify variable. Well, we do not have that variable anymore. And well, in this case, it did not happen because our bounding box is actually smaller than 2. So, but if we had a very big roof, very tall one, that would limit it. So actually, let me see if we have any roof that would satisfy to that condition. I don't think this is bigger than 2 either. So, but of course we are free to modify this. So let's say we want it to be bigger than 1, and as you can see, it immediately took the effect. So maybe 2 is a bit high number, but I'll keep it for now. You can tweak this number, make variables and make a handle that will drive that number. That's also possible. But for now, we'll keep it as is. So that is not the only constraint we want. Of course, we also want to make a random. So we will immediately put an and sign. And in here we say random. So random of what? Well, first of all, the probability. Then we want the random to be random in every case. And in this particular instance, I will make it run on endpoints. So endpoints of 1, endpoints of 0, and endpoints of 2. So I will just take all the possible points numbers and PT_num. So dependent on the resampling and dependent on the windows, not dependent on scatter because scatter always will have 100, but those two will kind of make our random seed. So that is all nice and well. So now if I apply it, and the node has a warning. Oh yeah, because we haven't finished. So we say that it should be smaller than probability. Apply. And currently we're not going to see anything because our probability is 0. So if we have 1, and as you can see, we start getting less and less points. So let's keep our probability 0.6. And inside of our if, we want to create a couple of integers that will hold our point cloud. So pcloud for our window. And we will create a PC open, second index input, channel P, original position, our position of point we're currently running over. The radius is 1.5 and 1. And we will do a pcloud for the edge as well. So PC open, 1 index input, P channel, original position is P, and here 0.8 is enough. You can also tweak those numbers if you'd like. And now we say that if PC_num found of our pcloud window plus PC_num found of pcloud of our edge is bigger than 0, so something was found either in PC_cloud window or in PC_cloud edge. That means that this point is wrong. We do not need it. So we just remove this point, PT_num, and that's it for our constraints. So as you can see, we immediately decrease the population of our points. So what now? We have all these points, but if we place chimneys on all of them, that will look very, very cluttered. So what we want is just we want to keep only one. There are multiple ways that you can do it. You can make another wrangle, you can sort it randomly. But what I like to do is I like to sort it by Y. So the lowest point is 0. And I like to keep the lowest point just because I like the look. It makes more sense to me. Maybe on the contrary, you want to keep the top point. It's up to you. So let's develop last node. And I only want to keep the 0. So delete non-selected, and here it is. But if we keep it like this, every single roof will have a chimney, which we do not want. That just doesn't make any sense. That would look, well, maybe in some cases, if you want to make a factory or something, that's the way to go, but not in this case. So I will make it 50-50. Again, you're free to make actually a global probability, but I will just make it a 50-50 chance. And I will base it on the number of points that are left in our pcloud. So it should be 50-50. And in this case, it didn't keep that point. But if we go up, look at our chimney, we go up. What can I see? Only this addressing. Thank you. And again, we run all the roofs. Yeah, as you can see, only one roof actually has a chimney now. So Since we initialized all the needed attributes, we can just merge these points of chimneys and windows. Merge, go up. Here again, merge, attribute init, everything is nice. And now we should place all of our modules. So, and as you can see, our chimney is nicely placed. However, since now, if we have sometimes two chimneys close to each other, you would be able to see that they are very repeating. And the one way to avoid it is, let's actually pin this view. Let's go back into our set dressing and our chimneys. And we will go back to our P cloud. And in our P cloud, we will add a random rotation. Add random rotation. So what we want is a quaternion. So let's grab a vector 4, called rotation, and it's a quaternion. If you're not familiar with quaternions, go to a Wikipedia page. But what it will allow us to do, we will need to grab a radians. And the way quaternion works is we will input the angle we want and the axis in second input. And this way we will tell it to rotate this amount around this axis. Let me remember what we are doing here. Oh yeah, we want to fit a value, which will be a random of our PT num. Oops, PT num. And we want to fit it between 0 and 1 because randomness goes between 0 and 1 and between 0 and 360. So after we have all of that, we want to tell which axis we want, and we want to rotate it around y-axis. And now all we need to do is have our normal. We want to tell it to q-rotate, which means quaternion rotation. And we tell it around which axis we want to do it, and how much about rotation, and apply. Oh, found a mistake. Very simple one. I just mixed up the location. So first we put a quaternion, and only then we put the. So now, as you can see, all of this chimneys are pointing in different directions. And if we change the seat, so if I get rid of this huge number I put in, yeah, they're different now. So that's all nice and well. So let's go back to our switch, and let's go up and up and up. And wait, not up yet. So here it's this one. Here is merge. We need to display all the correct nodes. And here we merge. And yeah, voila, that is our chimney, which is randomly rotated based on its point number in the P cloud. And yeah, that's it for the roof set dressing. So thank you very much for watching, and I'll see you in the next videos. Bye bye.
Hello and welcome back. This is going to be a short video where we're just going to tidy things up a bit, as we also neglected our global controls, as we currently have only one for the global. And also I noticed a couple of funny things going on, like here. When we have a smaller wall, we still get placed a full walkway, as well as the walkways they do not have the scale applied to them. Or actually, no, they should have a scale. It's just because of this particular wall, this got moved. So, as well as our cranes should also check whether they actually can pick something up from the bottom, because this crane just doesn't make sense. You can't really use it because those are used to lift heavy things up. So, we will start bit by bit. So, first of all, let's bring everything, also global controls in here. So, I did parameter interface. It got a bit outside of the screen, so let me show it. Oh, yeah, this one, edit parameter interface. So which ones would we need? So we would definitely need, let's rename this to a global seat. Apply. What we might also want to control is window probability, like a roof window probability. Roof window probability, and as well as we want we would want to control chimney probability. So chimney probability, and here also chimney probability. So apply, accept. So those two, and the chimney probability I will make it smaller, 0.2, and this one 0.6, and let's limit their range. So here a range from 0 to 1, and here from 0 to 1. Apply, accept. So let's start with the chimney probability. Let's copy parameter. And we will dive into here and get pivots and in set dressing and in chimneys. And here, this is our switch. So let's bring in the channel, paste copied relative reference, just cut it out, and in here, so whenever this is true, it will return us nothing. So let's invert that. So whenever this is true, it will return us oh yeah, now it's correct. It will return us the chimney. So if we only want 20% of the cases to return us true, we need to make sure that in most cases this random is going to be bigger than our channel. I mean smaller. So whenever this random channel is smaller, it will return us true and plus a chimney. So apply, accept. So another thing we would like to do is we want to grab the roof window probability and just go back into the set dressing, go to the windows, and here we should have our probability somewhere. Yeah, paste relative reference. So up and up and up. So that one is done. So maybe chimneys, we can make it a bit bigger number, but okay, that's fine for now. And another one we want to fix is with the walkways. So let's go to the stairs, and we'll go to the walkway and yeah, the bottom line. So here we have this in up because we have all this. Yeah, we do this, and what we want to do is, let me go back, check here. So what we don't want to do here is another constraint. So we want to add a measure node. We want to grab an area, and then we want to delete the small ones. So delete by area. So this is 2 by 3, so it's area of 6. So whenever area is smaller than 6, or let's make it 5, because sometimes our walls can be a bit smaller if it was created with platforms, so that can happen. So let's make it 5. And primitives, and ta-dam, those are deleted. And we only get this one. So this should be fixed now. Up. Yeah, that is correct now. And another thing I wanted to fix is the cranes. So let's go into set dressing. Oops, in our stairs, I see some really weird bug of our steps going in the wrong direction, which is kind of funny. So I know that why. In our steps wrangle, previously I was using this expression. It will always return you a positive number, so our stairs would always go into a positive direction. So all you want to do, because we want to keep others negative or a positive number, we just want to round an x and round and z. Oops, print. So apply and accept, and it should go in a correct direction. Merge it back, go up, place modules. So that is all correct. And we also want to fix the cranes. So let us get in here, crane. So yeah, so we have this point. So what we need to do is we need to bring the whole base. So let me think how we're going to do that. So we have a roof base, we have a body attribute. Let me check that. Yeah, we will kind of need both. So we need to attach those in here. We will merge them and we'll call it base. And we will connect it to the crane second input. And in here we will plug it. Let me bring all this way down. And we will plug it in here. And we will call it, actually we can, we'll put it in here. So delete to close. And in here, what we want to do is we want to check for the intersection. So let's do that. Check for the intersection with the body base. So in here, we will need a normal, so vector, like not normal, but array, I guess. Let's call it intersect ray. And it is technically our normal, but we also want to make it -1 in y because we want to point it down. But we want to grab the same z and x parameters. And now we will also need a vector uv and pv for our intersect function. So now we will just make an intersect function. So intersect with 1. Yeah, we need a vector origin, so it's going to be our position. And if I'm not mistaken, then we need to insert intersect ray, and then just pv and uv. Let me see if I'm correct. Yes, I'm correct. And so if intersect is not equals to -1, so it did intersect with something, then we don't need the point, so remove point 0 ptnum. Apply accept, and so it should be gone. Yes. Oh, just need to make sure that our intersection ray is a bit bigger because we technically want to write to infinity, so let's just make it 10. 100, and let's accept, and as expected, our crane is gone. But we can always get another global seed point. Sometimes some of them spawn, so let's keep that one. And up, and merge, and place. So yeah, now we have a crane here. Merge back. So we fixed all the things, and we are now ready to continue to the next part, where we will place windows and doors, as well as the towers. So I'll see you then.
Hello and welcome back. In this video, we are going to place our tower modules. So let's start by creating a null. And oops, there is an extra file here. Let's delete that. So null, the subnet, which we will call tower. We will color it to our dark blue shade. It will need a body base. And let's dive inside. So connect our null and call it in. So once we have that, our question becomes, where can we actually place towers? And for that, I developed 2 rules, which are towers can spawn in the places where roofs of the 0 floor touch the 1st floor, and of course on the midlines of the roofs that are on the top floor. So those 2 rules are the drivers for placing our tower modules. And let me actually find another seed that will have more cases for us to work with. I think number 17 would work nicely. Yes, because it actually has these points where the roof touches the next floor that I mentioned. And of course, we don't want all of the points because, as you can see from the top, there are 1, 2, 3, 4, 5 points that do that. However, this point and these points, they are on the outline of the building, which will result in our modules sticking out, and you would able to see that they are either end abruptly or they're actually hollow on the inside, which we want to avoid. So how do we isolate only the points that are subjected to those 2 constraints? So first of all, let's create a subnet where we will do that, otherwise our view will become very cluttered. So the subnet, we will call it tower inside points. Let's dive into it. Rename this into in. So first of all, we want to find the outline. So this is very easily done. We will blast everything except for the roofs. So we will call it roofs, and we will do it with the normals. So if n.y equals to 1, so the normals are pointing upwards, we want to keep those, and we want to transform them. So we want to merge them into one outline. Oops. And we will call it merge to the 1st floor, and we know where our 1st floor is. It's at 3 in y, and we will just say scale 0. So as you can see, it is placed correctly now. So what we want to do now is fuse the points, and we want to divide. So divide. We don't want the convex polygons, we want to remove shared edges. And ta-da! We have our outline. And we want to keep these points. So do not delete them, do not facet, and remove in line. So the next step, what we would need is to know where the walls are. And in here, we want to say that if ny dot equals to 0, that is our walls. However, we don't want all the walls. We only want the first floor. So let me copy this blast. And we will say top floor. And the way we're going to do it is, again, very simple. Just p.y should be 0 and 2.99. And that's what we have. But we also have this unnecessary extra points, which we're going to get rid of by using fuse. And as you can see, they automatically delete it because we have this keep unused points unchecked. So because if we check them, we would have them back, but we don't want that. So now we only want the bottom points. So blast again. Let's call it bottom points. And in here, we only want to keep those that are equals to 3. So delete non-selected points. And here we are. So now we will have a wrangle node because not all of these points we actually need. So we'll plug our outline, or let's actually call it border points. I think it makes more sense. And we will call this wrangle delete points that touch border. And then here, let's make it bigger and start coding. So it is a very short one, so it's just actually comment it out. We say delete the points that touch the border points. And it's very simple, as you might have probably already guessed by now. We're going to use a pcloud. So PC open. We're going to look at the points of our divide node at the original location at P, and very small radius, and we just need to find only one. So, and we say if PC num found of our pcloud is bigger than 0, so something was found, then we do not need this point because it touches our border. So PC num, we remove that point and apply and accept, and here we are. And let's check if that's correct. And indeed, those are the points that we want to keep. So that's very nice and great. Let's go up. So that is our tower inside points. So the next step is we want to bring in our middle line that we created when we were making the roofs, if you remember. So let's bring in object merge. So the next step, we want to bring our roof lines. Remember, we made those middle lines. However, we cannot bring those because they're inside of the loop, so we'll have to work around it. So what we want to bring in is our object. We want to look for roofs, modules, roof space, and then there is a roof attributes, accept. And why do we need the roof attributes? It's because they already have this very nice direction. Yes, that's what we need. The direction of their middle line. That's exactly what we need. So let's name it roof midlines, and we will color it so we can see that we are bringing something in from another subnet. So we want to recreate those middle lines with the attribute direction. But first of all, we do not need all of them. We only need the top ones. So what we want to do is we say p.y is bigger or equal to 6. And we want to delete non-selected, and we only want to keep the opposite points. Yes, so here we only have one. Let's name this to top floors only. Yes. And now we will bring a for each subnet, and we will recreate those midlines. So get midline for each primitive. So let's go inside. We already have only one primitive, and we will need to have our clip node. So in the clip, into our origin, we will put a centroid expression, and we want to have our dx, and here we want the dz. We do not care for y because we're going to cut on all y-axis. We don't need to specify, but you can if you want, of course. And the direction is our primitive, and we will access its direction attribute, and we want to reverse it. So in x we have z, and in z we have x, and here it's 0. And it's complaining because but not reference. Yeah, because it's each one. And here as well, each one. And we want to keep all the primitives. So here's our middle line. Great. But that's not it. We want to keep only the midline, so let's blast. And we will keep only 5 and 4. As you probably remember, these points are always the last 2 points. And since when we have 4, this will always be 4 and 5, which I explained earlier when we were creating the roofs. So delete not selected, yes. And we want to name it, so we say keep mid points. Next step is we want to connect them back by group, yes, call it connect. And now we want to resample them with a length of 1. And last but not least, because if we keep it as is right now, we have these endpoints. And if our tower spawns those endpoints, again, it's going to stick out and look very odd. So we will just blast those points. So it's a 0 point and it's a point that says endpoints. So the total amount of points of the resample minus 1. Delete not selected, so delete selected points, so yeah. And it's complaints because it's a resample 1. So yeah, resample 1. Nice. So here we call delete end points. So let's go up. So this is our midline. Nice and ready to go. So now we just want to merge everything together. So that is all the possible locations of our tower. And of course, we don't need all of them. We only need 1, because if you have more than 1 tower, again, it kind of looks very noisy because the tower is quite big. So the way we're going to choose is very simple. Just going to have sort. We will sort random. Let's actually connect it right away. We will grab our global seed, the parameter. And we actually need to put more stuff in there. So paste relative reference. So that is our global seed now. And let's actually name it to sort random. And now I just want to keep point number 0. Delete non-selected points, and we will call tower point. So what now? If you check the files which I attached, the tower actually consists of multiple modules. So now we have to assemble them, so to say. So let's bring a wrangle node, name it to tower, and the first thing you want to know for sure is the tower height. So how are we going to do that? For that, we will have to bring one more thing, which is our roof base. So let's connect that. Now let's create a null. This is our input, yes. We'll call it in roof base. Let's bring it down. Oops. So why do we need that? Because we need that because here we can see what is the highest point, and our tower has to be taller than that point. So let's bring it bigger and start coding. So first things first, we want to set the top points. So where is our top point set? Top point. How tall is our tower? So float BBY. So again, we will grab the bounding box. So that's a channel which we're going to create, and we call roof base BBY. So let's apply that, and let's create it right away. And here we just want to say bbox of op input path of the first index input, because we need the second input, and we want to know dy maximum. So it will tell us, yeah, it's 8.58036. Brilliant. So now we tell this point that we currently have that you are BBY plus random of that BBY, because, well, I'm a bit lazy to create the seed, but you can create a seed if you'd like. But I think it works fine because height will always be different, and that we want to fit between 0 and 1 to 0.1 and 0.3. So our roof is this value, and it always will be lower than our tower point by 0.1 to 0.3. So that's a random factor we are putting here. So now we need from that top point we need to create a set of points to populate everything with modules all the way down. But how far down? So at bottom points. So we need to know how far down it actually will go. So our intersect function only accounts for the first intersection it had, but we actually want to know all the intersections. So for that, we will create our usual PV and UVV, but this time they need to be arrays, because we will store multiple outcomes of our intersection because we will see all of them. And we will need the prims. And again, it will be an array because we need to know what prims were intersected. And now we can run our intersect. Intersect, yeah. And now we have this function that is called intersect all. And here we want to intersect it with the first index input. The origin location is our position, and we want to ray this intersection ray down to almost infinity, and PV. Then we need to specify where to store the primitives numbers in our prim, and UVV. So yeah, those are the tolerances. So now we need to find the distance between those 2 points. So find the distance between 2 points and resample if needed, because sometimes maybe we do not need to resample, who knows. So float distance is distance between our position and PV. So we need to access all the positions of the intersections, but we do not need all of them. We need the last one. So len of PV minus 1. So this way, we looked at the length of this array and we subtracted 1 because the array starts from 0. And this way, we are looking at the last component of that array. So now, float cover distance. So now we will create a loop. And I will need to have a cover distance because we're going to run a while loop. So we need to count how many we already covered out of the total distance. New point, of course, because we're going to create new points. And I like to make a variable x, and I will even comment to prevent infinite loops. Infinite loops, yeah. So, while our cover distance, the distance that we already covered, is smaller than our distance, and x is smaller than 10, because I don't want this to run more than 10. I don't think we ever will have a tower that will have 10 modules height. So just to make sure if something goes wrong, it's it's very annoying to exit this infinite loop. So let's do that. So cover distance is plus 3. Why 3? That's because it's our module size. I measured it and in Maya, and our module size is 3. And I will actually even show you because I think it sounds a bit abstract when I'm talking about it. I will just show you. So, what is our tower? So I think it's in set dressing. Yes. So tower, we have our tower body, which is this nice big chunk. And on top of that body, so the body can stack, we will have a top. So that's it. And yeah, I measured all these modules. So currently we are resampling it for body because this will just always go on top. So now we're figuring out how long should we stack those bodies together. So yeah, and that body height is 3. So new point. So at point, it's a 0. And it's our origin location minus set 0 cover distance 0. So now we are subtracting from our origin position and we are lowering it by the cover distance and we're creating a new point. That's what we are doing. And we will set a point attribute, of course. And we will set it a name. It's a new point, yes, and we're setting the name tower body set. And x++, so we don't run into the infinite loop. Yes, that's all nice and well. And of course, what is our origin point? That's very simple because our origin point is already there. And you might have probably already guessed. Yes, it is tower point. So tower top. I mean, yeah. So that is all nice. So let's apply and accept. And let's see what we have. And yes, we are running all the way to the last intersection. And you probably say that we actually covered more than our distance, which is fine. Like, we do not actually need to go it exactly here. We will never need it because it will already intersect with the roof here, so it is all fine. So, it is all beautiful. So now, let's place our modules. But before we place our modules, of course, we need to initialize more attributes. So, I will put it in a separate triangle. You can put it in the same one, but I just think it's the logical division. And put it in it. So, here, we of course want to tell it that its type is a set dressing. And its variation is 0.1 because we do not have any other variation. If you do, just repeat what we did when we had multiple variations. Its scale is actually, I made it a bit too bulky, so I actually scaled it down here to 0.8 in X and Z. And now we want to add random rotation, just like we did for our chimneys. So we actually do it. Yeah, that's all good. So here we will need a vector position. And why would we need a random vector position? I use it for our random seed. So when I have a float seed, you of course can just create a seed. Why not? I just like to tie it to these kind of things. So we just run as the amount of points we have, plus position X, plus position Y, plus position Z. So it works perfectly for our seed. So again, we have a vector 4 rotation, which is a quaternion, yes, quaternion of a random of seed plus whatever 90. And we want it to be a fit between 0.1 and 0,360. And did we close it? Yes, now we did. So, and we want it to be radians because it requires radians. And we will rotate around y-axis, yes. Oops. So our normal is a Q rotate. So our quaternion goes here and our initial vector direction goes here. So apply and accept. And now, as you can see, they all pointing somewhere. So let's check if it works. Plus 6. Yes, it works nicely. Yeah. So now there is a couple more checks you're going to run. First of all, sometimes our building is actually smaller than the top height. So that might happen just one floor. So we want to make sure that we'll never have a tower if it is only one floor. So let's create a switch. Let's create a null. Call it check for height. In here, we want to make sure that bounding box of n dy maximum is bigger than 4. So it is, if it is bigger than 4, no, in this case, let's go find this, then it can indeed exist. So we need to make sure that this n is bigger than 4. So well, if it is 2 floors, it's going to be 6. So 6 is bigger than 4, obviously. So that will work. So check for height. That's a good check. And now again, we want to have a probability. So switch. You can make a global control for probability, but I will just, again, tie it to the things we have here. So I will just say probability, and I will say that random of endpoints of check for height plus endpoints of in is smaller. Well, actually, yeah, let's tie it to our global control. So our global control will go up, and we will go up. Yeah, and we need this out. No, not create quality. We need out, and there we will create a tower probe. Now, right now it doesn't exist, but we will create it. Find accept. Yeah, it complains that it just does not have it. So let's edit parameter interface. Well, you don't see it here, but yeah, this one, edit parameter interface, and we will create a float which we will call tower probe. And we'll call it tower probability. Well, here we will always name it probe, so let's be consistent. Line accept, and it's a file, and it should be a float. Of course, it should be a float. Line accept. So right now it's Well, we can go all the way up to 10, which is not what we want. We want to go from 0 to 1. Yes, thank you. So let's make it something like 0.4. Well, it still exists. Oh, because are we not looking at the last switch? Well, we are, but it still complains that there is no tower probability, which is clearly not the case because we just created it. Tower prob. Let's copy it and just make sure that maybe I didn't spell it the same way. No, now it does not complain. Well, yeah, and the tower does not exist in this case. So let's go for 4, and it still does not exist, so which is fine. So this tower, and we have all these points. For now, let's just check for height here so we can actually see the result. If we keep everything, it's going to be very cluttered, so I'm actually going to create a subnet. Which I'm going to call get pivots, because it also has the pivots for our tower. And we're going to copy our place modules from somewhere else. Let's copy it from roof modules. Place modules, copy that, thank you. And that is our tower. Let's merge it with everything else. And that's what we have. And as you can see, it looks a bit odd because it's kind of very close to our windows. So how are we going to check that? Well, we do have to check for that. So we do not want, of course, to bring all this heavy geometry into checks. So what we're going to do, we're going to create a null. We're going to create a subnet, which we will call power check. And since it's only for checking, we will make it a gray, so it becomes kind of invisible, like you know that is something not important. So in here, we just want to copy on those tube, which is a polygon in 3 height, 9 rows should be enough, and about, well, 8 I think. Yeah, beautiful. And that tube, you want to copy it. Oops. On the contrary, yes. And we want to make sure that it actually stands on top. So let's grab copy parameter, paste relative reference, divided by 2, because that's how our module pivot is, bottom center. So yeah, that is the geometry we can check. So let's go up and we will go back into our roof modules. Go back into get pivots, set dressing. And in here, we're going to bring our tower, so object. I'm going to bring our tower. Where is our tower? So, yeah, our tower, and we will get this tower check. So, tower check. Let's color it so we know that we're bringing something from another subnet. And we will create a wrangle. And in here, we'll connect it here. And we will call this wrangle check for tower. So actually, we'll see if we have any points. No, not really. Not now, but let's bring this bigger. It's a very simple check. Again, we will bring a pcloud, PC open, and first index input, p channel. We want to run it from the position of our point, radius 1, only 1 point. So if our point in a radius of 1 sees a tower, then we do not need it either if it's a window or if it's a chimney. So apply and accept. So right now we're not going to see anything in here, but if I go up again, and we merge everything together, as you can see, all the windows disappeared from this roof, which is exactly what we want. And you might complain that the tower looks a bit synced into the roof, but don't worry about that, because later on we will have to implement the crooked look, which will make the whole building synced in, but the tower will not be affected as much. That is the way we're going to compensate for that. So don't worry about that. Everything is according to the plan. Oh, and before we go, almost forgot. Very important things, because sometimes our tower can be on the very different position, which is, let me illustrate to you that position. And I already see a misspell. So tower point, so let's see which points we have here. So I will actually make it point number 2. So let's imagine that our tower is here. So when it's placed, up, up. So when it's placed here. And well, here we are lucky, we already have this walls gray, but if we would put it here, yeah, I guess that's a better example. Sorry, let's go back, and it complains because it cannot find out. I think it's because we made a subnet. Let's see. Yeah, now it's fixed. So we just, because we created a subnet, it lost its connection. So, but yeah, we need this point. Let's grab a point number 1. I think that's a better illustration of what I mean. Yes, and you see it placed windows there. And if we actually put a window there, it will be very, very awkward. So it's a very fast fix. So in here, when we check for no windows and we have this locate roofs, we will merge it with our towers check. So tower check, where are you? Tower, yeah, tower check, here it is. We're gonna merge it. I'm gonna say that it's tower check. Yeah, we call it and named it. It's all good. So we have this. Yes. So in here, since we are checking from the center of the primitive, we would have to make it a bit bigger. Oops, not torus. I'm typing tower. Oh my god. Transform. We need transform. And what we need in this transform is, well, from the center of our figure, we will enlarge it in Z, in X and D. So it was like this. It became like this. So it definitely abstracts the windows. So when we have a check, you see that it's, yeah, it abstracts it. Very nice. That is exactly what we want. Very simple fix, right? So now we just make sure that there are no windows there. Otherwise, yeah, awkward. So yeah, that is it for this video. And I'll see you in the next video. Thank you for watching. Bye-bye. Hello and welcome back. In this video, we're going to place windows and doors. So let's start by, okay, we do not need this merge. So we will start by creating a null. And we will connect body attributes to our null and create a subnet, which we'll call body modules. We will color it in a darker blue shade and dive into it. So let's rename it to in. So in here, we will grab a for each subnet right away. It will be our big main body loop. So let's call it main body loop. Inside of that loop, we will be placing doors and windows as well as generating the geometry for the walls, but that we will cover in the next volume. And in this one, so we will focus on doors and windows. So let's set it for each number. It will be easier for us to show the examples. So let's grab a number. We will start working on the doors. So yeah, currently it's running 10 times. So any number of the door to 12 or 15 in my case. And if you have any other seed, make sure to grab a blue door primitive. So 12 in my case. And I will color this subnet right away so we can see that it's important. And let's dive into it. So what do we want to do inside of this loop? Well, let's have a look at what we have in our files and what we have to place. So if you go to modules and body, you can see that we have door cut, door frame, and door plane. And the same for windows, except it doesn't have a plane. And let me show you what it is. So what is a door cut? A door cut is a special geometry I made to cut out the doorway from our wall. So if you look at the frame, other way around, it perfectly corresponds with our cut geometry. So those cut geometry are made specifically for a certain door frame. And that is important because they have to have the same number. That is the first rule we have. So if I change this to number 2 and this one to number 2, you see, they perfectly fit into each other. And if you're working for games and you need it to be modular because we're going to cut out procedurally inside of Houdini, make sure that you actually have a module with a wall and the correct cutout. So you're not actually placing the cutout itself, but you are placing the module which already has the correct cutout right away. So in a way, you're skipping that step and making it manual. But we're going to do it inside of Houdini. So let's dive into it. And oh, one more thing, and that is I have the same numbers 1, 2, 3 for both doors and windows 1, 2, 3. I made it for my own convenience because this way I have to generate the variation only once without actually looking whether it's a window or a door. But if you have different number of variations for those modules, make sure to run a special check or do like I did. It's a lazy way. Make your life a bit easier. So let's go back to our H. So first thing we want to do is we want to locate the primitive we're currently running over. So let's grab a blast and we're going to do it as we do it usually. So let's name it locate and we're going to run a stamp function. Stamp up for value since we haven't renamed our stamp name. And we're going to say it's for a primitive and delete non-selected. And for some reason it gives us this, which is incorrect. So I think if I go up, yes, it automatically updates. So I will actually pin this view and I will go back. And in this locate, the next thing I want to do is we want to grab the centroid. We want to know the pivot position of our modules. So for that, let's do it with a transform node. So let's grab a transform node. And then here, we're just going to place central pivots. So $CEX and CEZ and CEY. And we're just going to say that scale is 0. So we'll call it get centroid. And now we just need to grab only one point. So we will call it centroid. And literally any number from 0 to 3. So let's grab a 3, delete non-selected, and it's a point. So that is all nice and well, but we need to grab our attributes that we have in here. So if you go to our locate and you go to primitive, we have very important thing, such as the type. And we need to grab that. So let's bring a wrangle node. We will connect our centroid point into the first input and our locate, which contains our primitive with the attributes, to the second input. We will call it attribute initialize, so attribute init. So run over all points, or well, once, because we only have one centroid. So let's bring it bigger. And in here, we will identify multiple things. First things first, let's grab that attribute. So we let it run only if it is not a wall, because if it is a wall, we don't need to place anything. So to check that, we're gonna say that if primitive from the first index input, so from our primitive from locate, and we're gonna look at its type, and we wanna ask, it should not be a wall. So if that is satisfied, we can continue. So we want to identify the type, which is body. Oops, body. We want to grab the name, which is the type of our primitive. So let me just copy that here. Yes. And we want to identify the variation right away. So variation, because we need to know which module to actually place. But for that, we will need a couple of things. First of all, we'll need a seed. So float seed is channel seed. And we will need to create a random number, so int variation, and it's going to be our random of seed. We just do it absolutely the same way we always did it. So random of seed, we want to fit it between its original 0 and 1 to 1 to 3. We want to rint it, and we need to convert it into an integer to prevent a node warning, so int. So our variation is 0 plus printf, so we're converting this to a string, our integer into a string. We're gonna say that place our variation variable, and yes, that it will be converted into a string, so all nice and well. And else, so if it is a wall, we do not need the centroid at all because we're not going to place anything. So remove point 0 fits in now. So apply and accept. Let's create that seed. And we need to connect the seed to something. So let's create a null, which we will call seed. Let's color it. And it still cuts out a bit. Wait a second. So like this. Edit parameter interface, yes. And in here we want to grab a float. We will call it body seed. And here just seed. Apply and accept. And for this seed we want to grab first of all our global seed. So let's go all the way up. That is our out. So let's grab this copy parameter. Let's go all the way back. Let's paste copied relative reference. And from locate, we will grab the stamp because we want to have our seed have different numbers in every loop iteration we have. So plus our stamp. So that is our seed. So let's copy parameter and place it into our seed over here. So currently our seed is 17. Let's actually grab a random and just multiply it by 100, something like that. So yeah, awesome. So let's color it into a yellow color so we can see it. And this point we have here is going to be a driver for all of the modules we're going to place on it, including our cutout. So let's actually start with cutting things out. And for that, we will need to grab a grid. And this grid will act as a wall. So we don't want any divisions in it. We want to have it in XY plane, yes. And the size is going to be driven by our locate. So we're going to actually have absolutely the same size as our input wall. So how are we going to do that? Well, first of all, you can immediately see that they have different orientation. Let me unpin the view. And it still shows us the wrong one. So let's not unpin the view. So yeah, you can see that they have different orientations. So the way we're going to deal with it is, well, Y is quite simple. So let me first do the Y. Y is bounding box of our locate. And it is dy maximum. And let me copy the whole expression. Minus dy minimum. So that is simple because our Y does not change based on the orientation of our wall, but our width does. So how are we going to deal with our width? Well, that is quite actually simple. We're actually going to just take x maximum minus x minimum, and then we're going to add the same thing, but the z-axis. Because if one is equals to 0, then other cannot be equals to 0. The other will be our width. Because our wall is infinitely small. So if, for example, it has width in z-axis, it's going to be 0 in x. So we're just going to grab both of those and apply and accept. And as you can see, we have our 2x3 wall. Absolutely perfect. So now we will place our cut module and cut things out of this grid. But before we do that is, if you grab the file and you will look at it, you see that we have door underscore cut. But if you look at our spreadsheet, the way we named our point is just a door. And that's because we're going to add additional information to it, which we're going to do now. So let's grab a new wrangle. We will call it cut attribute because we need to add that. And we're actually going to also color it. And it is very simple. I'm not going to even make it larger. It's literally one small line. So S name is plus equals. So we add to the end of it cut. So that's it. So now this point has all the information we need to place our cut module. So let's actually create a null, convert it into a subnet, which we will call cut out, and let's color it and we will plug our grid into the first input and our cut point into the second one. Let's go inside. Let's name our null in. Let's copy it, plug it into our second input, and we will call it cut point, because that's what it is, cut point. And now we'll grab our file and we will write where to find our cut module. So yes, it's in heap modules. Then we're going to write point s because it's a string. We're going to look at our cut point. We're going to look at the very first point and we're going to request to look at its type. So let me copy this expression. Then we have underscore. Again, we put the type, underscore. Then we put a name. Again, underscore. Then we put a variation. And don't forget to type .obj. So apply and accept. So and yes, we have our cutout module. So let me actually check what is our variation. Okay, not in here, but in our cut point. Our variation is 0.2. So let's actually see, does it work? Let's spin our view, let's go up, and we will change the seed. So here, well, actually, let's change it when we're running in the wrangle. So plus 34. That is curious. Oh, I see what's happening. I was like waiting for it to be a door, but I guess our update is not working correctly again. Because when I'm going to seed and relocate, so yeah, that says a door. And it is a door name. Yeah, that's all correct. So we have a cut point and then we place, yeah, so now it's correct. Yeah, something was wrong with the subnet updates again, so sorry for that. But yeah, that's what I was trying to prove. So now if I put another number, hopefully it will show you, yeah, it's changing to something new. So let's actually keep our 12 because I like this shape. So let's see what we have. So we have this door cut and we have our wall. And I immediately can spot a problem that the normals of our wall are pointing into the wrong direction. So we have to fix that. It's very easy. Let's just grab a transform node and just ask it to rotate 180 degrees in Y. So now our normals are pointing in correct direction. And we can merge our cutout and our wall together. And please note that I have a bit of space here. And that is not accidental because I'm going to use whole node. And yeah, it doesn't work because we are not at the same position. So to ensure that, let's bring a transform. And we will just say that it is 0 in Z. So that perfectly lie on each other. So now the whole will just cut everything out. And note that it wouldn't work if our door plane exceeds the wall. So that's why I have a bit of space here left. And in this case, we didn't have any problems, but sometimes if you have edges in the cutout geometry, it complains or does cutout wrong. So make sure to have a divide node in here. And we don't want to convex. We want to remove shared edges. Yes. So that should prevent the problems. So now, let's see if it works for other cases. So if we go in, so currently we're not placing it at the same position, so it's just going to be on the 0, 0, 0 in the center of our world. But let's just see, would it work with our windows, for example? So 19. And yes, it does. You can see it perfectly cut out a very nice small area for our window frame. But would it work with our wall? That is very important to check, and I already know the answer. Do you? And it wouldn't. Why wouldn't it work? Because we're not doing anything, right? Well, actually, we are still going all the way through to our cutout. And in here, since we do not have a cutout point, it doesn't know what to place in the file, so the file node complains. But for that, we just need to make a very simple switch. We want to tell it to just skip all of that if there is nothing in our cutout point. So let's say that endpoints of our cut. Oh, I forgot to place this one. So cut point, yeah, endpoints if it equals to 0. So in this case, it is true. Then we just want to skip all of that and just place our wall because, let's face it, that's all we want. We just want a wall. So that's it. So now it will work for everything. So let's go back to our door, so number 12. And now I want to place it back on its position where it used to be in this locate. I want to have it the same position and orientation as its original parent, so to say. And how are we going to do that? Well, yeah, you can use copy and stuff, but I want to show you another way because sometimes you might not want to use copy. So how are we going to do that? We're going to do it with vex. So the first thing we want to do is you want to know what is the rotation of our primitive compared to the z-axis. So why z-axis? Because our modules are pointing in that direction, like its default normal points in that direction. And then we transformed it somehow on some arbitrary number and we got this. So we need to know what was that number. So we want to grab a wrangle. You don't need actually to have a separate wrangle for it, but I want to separate it for the purpose of making it easier to digest, so to say. So we will call this angle. So how are we going to find angle? So let's actually bring this bigger. Well, we're going to use dot product. So what is dot product? If you go at math is fun, that is what we need, which is the dot product. You will get the length of these vectors multiplied by its cosinus. Aha, cosinus. That is exactly what we want to find our angle. It is just absolutely perfect. So let's implement it in Houdini. So we will grab float angle, and that's what we want. So we will grab dot product of our normal that we're currently having. So this one, because we're going to run for every point. And our axis that just goes in Z, because we know it's default. So we don't yet need to plug anything else in there to check that. And we just don't want just the dot, because currently if we do that, we get our cosinus value. So we do not want just cosinus value, we want the angle. So let's arc cosinus that, and we will get radians. But again, radians is a bit not very intuitive, so let's actually convert it to degrees. So degrees, nice. So our angle is angle. But if you do just that, and let me show you again. So let's take a very simple example. Let's say our cosinus was 0. However, as you can see, there are two ways we can go. So, for example, if we actually limit it from 180 minus 180, we have two values for our cosinus that equals to 0. So which one to take? Well, Houdini doesn't know. It will always just return you as a positive one. But we have to account for that because those are actually two very different things for us. So to do that, we need to check whether in.x is negative or and.z is negative. Because if either of those values are negative, we just want to invert our angle. So 360 minus angle. So that will fix it. Oh, angle. Or, well, technically it doesn't matter because it's the same thing. So apply and accept. So let's check if it works. Let's go to our spreadsheet and we should have our angle. And aha, it's 90. So let's check if it works. Let's check if we are right. Let's prove it to ourselves. We will go and take our transform. We will take center pivot. And we will rotate minus 90. Aha. So we are right indeed because we rotated it minus 90 and we got our default orientation, which is just 1 in Z. So that is correct. All nice and good. So now we can just grab a new wrangle because that is just one step because our initial goal was to place this in its original position. So let's plug our cutout into our wrangle. We'll call it rotate and transform because that's what it does. and translate, rotate and translate technically, because transformation is a combination of all scale, translation, and rotation. So let's color it so we can see it. And in here, our angle will go into the second input, and we also want to grab our centroid, because our centroid shows us the location. It shows us how much we have to translate. So let's bring this bigger. We'll run it for every point because we're going to transform every point kind of separately. But it will be so fast and we're going to see it. It will seem very instant, and if we are transforming the whole thing at once. So what do we want to do? Well, first of all, we want to get our rotation, and then we want to get our translation. So with rotation, it's simple. We already know the angle. We just need to access it. So it's the first index input. We have our angle attribute, and from the first point. That's good. As for the translation, also very simple. It's a point from our second input. Channel P, also the first point. So, but how are we going to actually apply it to our position we have now? Well, first things first, we need to identify a matrix. So matrix, we will call it transform, and we just need to make an initial state for it, so to say. So ident. So what is ident? Well, if you multiply this matrix with our position, nothing will happen. So that is what it does. It just will do nothing. But we need to first have at least something to do what we need. So once we have that, with our rotation, what we want to do is we want to rotate on that angle. Well, first, what do we want to rotate? We want to rotate our transform matrix, and we want to rotate our transform matrix on radians, because it calculates in radians of our angle. And we want to rotate around y-axis. So now if we multiply our position with the transform, apply and accept, you can see we rotated our module onto the same orientation as our original module. That's good. So now all we need to do is just add the translation we have. Why do we just adding? Well, because our pivot is in the center, so it doesn't have any translation applied. That is why if we just add the translation we have here, it will be correct. Well, it should be correct, but I think this update is messing with us. That's what's happening. Let's see. Oh, I found the error. I put a float here. It's a vector. So sorry for that. So apply and accept. So now it is correct. And I have a merge here because I was just testing whether it's placing on the same position. So we actually don't need to make this merge. And yeah. And actually, this is not a transform because translation we do separately from the matrix. So I will just call it rotation. And that will be less misleading. So apply and accept, yes. Oh, good. And as you can see, our normals are now very weird. Why is that? Well, because we're not actually updating them. Because copy was doing it automatically for us. But here in our Wrangle, we only deal with the position. But it's a very easy fix. All we just need to do is grab facet node. And we just ask it to post compute normals and we have them back. So let's actually see whether it works for everything. That's not yet everything. So and prims of input path 0 and -1. And ta-da! Everything works perfectly. And as you can see, we have different types of windows here. We have different doors as well. Well, just the cutouts for now, but that's already a start. So that's great. And in the next video, we will place all the rest of the modules. And I'll see you there. Thank you for watching. See you soon. Hi, welcome back. Let's continue placing the doors and windows frames and all the modules connected with that. So let's go back into our main body loop. And in here, when we have our centroid point and our attribute initialize, let's actually grab it a bit to the side So we have more space to work with and it looks a bit more organized. It's a bit here. This is here. Yeah, great. And what we want to do is we want to grab a new wrangle. So attribute wrangle, and we will call it frame attribute. And before we write anything, I want to actually show you what parts our doors and windows have. So if it is a door, it has a frame, it has a plane, and that's about it. But if it is a window, it has a frame, so both of them have a frame. But instead of a plane, it has a shutter. So that means that frame will be present for both of them. However, plane and shutter will not, so we have to write the constraints for those. So as for the frame, it's very, very simple. So our point, yeah, it's runs over point, it's great. We just say if s name is not equals to nothingness, we say that the s name, and we just add that it is a frame. Just like that. And let's color it to an yellow, and we just copy it 3 times. So 1 and 2. Well, 2 times. Still 3 in total. And the middle one, we will rename it to shutter attribute. And this one is a plane attribute. So in the shutter, let's make it bigger. We want to write different conditions. So we want to say that if the name is a window, so we are currently checking the window, we want to add shutter. However, if it is not a window, we do not want anything. So remove point 0 ptnum. Oops. No capital letters, ptnum. Yes. And apply. And very similar. So I'm actually even going to copy that. And then we will put it into our plane. But here we want to say if it is a door, then we want a plane. Plane. So apply and accept. So what we're going to do now with all these 3 points, we're going to merge them. So let's bring merge, and we will connect all 3 to the merge. So currently, and let me actually make it run only once. So we're going to actually cut out this expression and just place it temporarily into a transform node. And then here, let's grab 12 so we know it's a door. So yeah, it is correct. We have 2 points. So now, with these 2 points, because those are actually pivots with the correct naming and everything, we want to place modules, just like we did all the time. So for each subnet, we're going to name it place modules. Since we are running a loop instead of a loop, we need to rename it, otherwise it's going to conflict. So we're going to say, well, modules and modules, and we're going to run it each number for the number of points we have. So points of input path, yes, of 0 index minus 1. So we should run it from 0 to 1. Yes, correct. Let's go inside. So in here, we want to locate again. So we're going to say that when the same point as the stamp of up and for value modules 0, close it, and yeah, we have only 1 point now. Awesome. So now we just want to grab a file, and let's select anything. So we have the foundation where we can write, and in modules, I'm actually going to copy it from our cutout because I don't want to write that huge expression. So we're just going to copy this. So Control S, go up, go back into our place modules, and in our file, we're going to place it. Yes, and place it. So complaints, because, oh yeah, when we copied it, we are running for cut points. So let's just rename our blast to cut points so it connects to that. And now we can just safely rename it to locate. So we have our shutter. So I guess our update again gave us a window instead of a door, but oh well. All we have to do now is bring a copy node, and we're just going to copy our module onto our point. Yep, that's as easy as that. So as you can see, we have our window, and we have only one shutter for now, but I will explain in a second why. And what we want to do now is just merge our cutout wall with our modules. And as you can see, it's freaking out, but as soon as we go up, it updates correctly, and we have our door frame and our door plane. So if we do it for not for everything, let's do it from 0 to 12. As you can see, everything is nicely placed. Well, that's what you will see if you look from the inside of the building. But yeah, on the outside it looks fine. So now, the problem we have, well, yeah, not a very problem, but let's say visual issue is that we have only one shutter. And that's not what we want. We want two shutters, and yeah. And we also want to make them randomly closed or opened. So how are we going to do that? Well, if we go back to our main body loop, and we go back to our place modules, and here comes the fun part. We will create a separate subnet for our shutters, which will trigger only if our point is a shutter. So since now we don't have a shutter, I will actually copy a file and I will take a shutter so we have something to work with. So shutter number 1 is fine. If I can select it, please. Yes, thank you. So here's our shutter. So I will actually put it here. So first thing you want to do is we want to randomly rotate it. So let's bring a transform node. And we will call it rotate. And what is the pivot of our rotation? Well, it's actually not this one, definitely. It's on the top right side, so somewhere over here. So in our pivot, we are putting x minimum because that is our pivot here, and you can see it actually moves this point. And it's y maximum, and it's z maximum. So that is our pivot where we're going to rotate. And actually, this is a facing axis, so it's going to face it like this. And what is our rotation? Well, we can just go up and we can grab this seat, or we can actually connect it to our position, which is also a valid thing. So that is kind of a choice you have to make, but oh well, let's actually make it with the seat, because in my own network, I usually make this point position, but it's always nice to change things, so, and try something new. So let's put that in our rotation, because we're going to rotate in Y, as you can see, it nicely moves. And so paste relative reference, Alt E, and this is our channel. We want a random of that channel, and we don't want only that channel, so let me apply and accept. We also want the stamp of our point. So, well, technically, it's actually not going to matter if you think about it. Now as I'm thinking about it, because we're always going to have maximum of 2 points, so you can actually just neglect the stamp completely and have it only with our seat. So let's do that. So what is the rotation we want? Because let's actually think about it. Because if we just rotate like 1 degree, no one ever is going to notice that. So let's actually have a minimum rotation and figure that out first. So fit 0, 1, and well, let's say 20 is going to be our minimum. I just want to see how it looks. That's why I put 20 and 20. And the first thing I see is that it has to be a minus. So let's put a minus. Let's put a minus before F. That would be great. So yeah, well, 20 I think is good enough. I think we should start at 20. And what is the maximum we can open? Well, 180, I think it's a bit too much, maybe 160, and I will put it in here as well. That's what I just want to see how it looks. Yeah, it's like wide open, so yeah. I think those numbers work well. You are free to tweak them if you want. So 20 to 160, that's good. That is our rotation. So once we have our rotation, how are we going to actually have the second piece of our shutter? Because our shutter consists of two pieces. So, well, that's also very easy. Let's bring it transform. And we're going to say, well, how are we going to call it? Let's call it mirror, though it's not technically mirroring. But what we're going to do is we're going to say -1 in X. And right now, we do not see any problems. We're not even aware of them. But if you look at the normals, they're incorrect. Like, as you can see, these ones, they should point upwards, but they're pointing inwards. And to fix that, we need to bring a reverse node. And in reverse node, we need to say reverse. Fixes that. So let me actually check. Post compute normals, and without it. Yes. So yeah, as you can see, there's a difference. So if we place a facet node and we say post compute normals without the reverse, it just, yeah, makes it absolutely incorrect. But with the reverse, it's back to correct again. So we don't need facet yet. So now we just can merge this shutters together. So merge, merge. Yes. Perfect. And if you want this to have a different rotation, you can just create another rotation node and make a different seed. But I like to have them mirrored. So that is one case we have here. But we also want to have a case of them closed. And it's also very simple. Let's just copy everything we have here, actually. And we just disable the rotate. We just do not need it anymore. So, well, actually, I'll keep the rotate because it makes it tidier. So I'll keep that. And now I want to switch between them. So switch. So which case are we actually using? And again, we can just grab our body seed. So copy that, bring it into our switch, and just have a different number here, like 56. And don't forget to close the bracket. And yeah, now we have a 50-50 chance of them being closed or open. So let's keep them open in this case. And now we also need to make another check. And what is the check? The check is, are we actually running on a shutter? Because if you just take what we have now, let me see what it is. Well, we actually have a shutter, but if it was like, I don't know, a window frame, that would look very, very weird. If we're just mirroring it and rotating it, that wouldn't make any sense. So we need to check for that. So let me plug our correct file node, delete the unnecessary one. And now we just want to make another switch. And remember, the switch doesn't like strings. So unfortunately, we cannot check the type. But in our locate, we can cheat a bit and make a wrangle. Just like we did with tower, I believe. I believe it was tower. So it will be called switch check. And all it's going to do is look at type if the name. And if the name is a window shutter, it's going to make a switch of 1. So switch equals to 1. So now it should give us a switch of 1. So let's check that. Yes, switch is 1. And that attribute, since it's not a string, we can actually input into our switch. So our switch, and we're switching between all of this. So let me actually make a box. Not this one. I think it's this one. Yes, net box. And we will call it shutter. We're going to switch between the shutter, netbox, and our file. And in switch, we're just going to ask it point. The point is a switch check point 0. The attribute is name switch and 0. So if the switch is 1, then we want to have our netbox. Yes, beautiful. And then we want to place this whole netbox into our copy node. So let's see if that worked. So let's go up and up. And ta-da! Now we have 2 shutters. So these ones are closed. This one is open. So yeah, let's actually try changing the seed. So I'll go back in there, place modules. Yeah, this one. And let's say 567. And yeah, as you can see, now different one is open and these ones are closed. And if you want a different probability, not just 50-50, make a handle in your global control, the out node in the very beginning. But I'll just keep it 50-50. So yeah, let's go up and up. And now let's place everything. Let's take all the primitives and see if we have any issues. And no, we do not have any issues. So we have nicely placed doors with the correct cutouts. Some of the windows are open, some of them are closed. We have both shutters and everything is just beautiful. Nicely done. So I'll delete this transfer mode node since we do not need it anymore. But yeah, that's it for the procedural modules placement. Congratulations on getting this far. And so let's actually go up and see everything together. So now we can actually unplug our body attributes and we can plug our body modules, and let's merge everything and see how it looks. Oh yeah, I'm waiting for it to do something and I was like, what's happening? Oh yeah, I didn't unpin the view. And yes, that's what we have now. Nice. Very, very nice. So yeah, that's it for this video and for the volume number 3. And in the next volume, we will start generating all the additional geometry to give our building a finished look. And I'll hopefully see you there. Thank you for watching. Bye bye.